Imagine rain that never stopped, not for days or years, but for 2 million years. During the Carnian Pluvial Event, endless storms reshaped Earth and changed the course of life itself. Tonight we'll uncover how this ancient rainfall transformed our planet. If you enjoy this story, please like, subscribe and share, and tell us in the comments, could you survive a world where it rained for 2 million years? Thank you for watching. Now, let's begin. Pangaea stands as a single linked landmass that reaches from high southern latitudes across the equator into the northern hemisphere, a broad mosaic of ancient cratons welded along long sutures and rimmed by intricate margins. Its outline in this late Triassic scene is wide and irregular, with headlands, gulfs and peninsulas that face long stretches of open water. To the western north lies Panthalassa, a planet-spanning ocean whose swells can run for many thousands of kilometers before breaking on rocky capes or shelving plains. To the east and southeast spreads the Tethys Ocean, a connected realm of embayment straits and island arcs that divide basins and funnel water between narrow passages. In places, the eastern margin is protected by microcontinents and arc chains that create partial barriers, while in other reaches the continental edge meets deep water with little shelf to slow the sea. The supercontinent shorelines are not simple lines but crowded notebooks of promontories, inlets and ramps that mark where the land invites or resists the ocean. Relief on Pangaea adds a further layer to this frame. Uplifted belts rise where earlier collisions stacked crust and left deep roots, and low plains spread where older basins have long subsided. The central Pangaean mountains run as a long swell near equatorial latitudes, tapering into highlands that grade into broad plateaus. South of the equator, stepped surfaces span what will one day become the southern continents, their edges dropping into basins that collect sediment shed from nearby scarps. Farther north, terrains align into ridges and forelands with narrow corridors that guide drainages toward continental interiors or out to sea. These patterns of height, slope and width set the directions in which water can move and the places where it can pause. The presence of plateaus beside lowlands produces contrasts in potential energy that prime the landscape for long journeys of sand, silt and clay from upland to shelf. The oceanic boundaries around Pangaea are just as structured. Beneath Panthalassa, spreading centres and broad rises keep some tracts of seafloor high and young, while older crust subsides and deepens into wide abyssal plains. Seamounts and guyots punctuate these plains, adding roughness that can steer deep currents along fixed paths. Along the eastern realm, the Tethys hosts accretionary prisms that fringe active margins, while volcanic arcs track the lines of subduction. Narrow straits cut between microcontinents and allow water exchange from one subbasin to another. Trench systems sit beside some continental edges and hold the deepest parts of nearby basins. At passive margins, continental shelves grade gently into slopes and then into the abyss with shelf width, varying from narrow rocky benches to vast shallow ramps tens to hundreds of kilometers across. Where shelves widen, the sea can remain shallow far from land, and where shelves narrow, deep water approaches close to shore. Coastlines around the supercontinent alternate between rocky highlands and low-lying plains. In rugged sectors, shore faces lie close to bedrock wave energy is focused, and sediment storage is limited to small pockets. In gentler sectors, strand plains, barrier systems and deltic fronts construct wide lowlands that migrate as sea level and sediment supply change through time. Along parts of the Tethyan margin, clear and well-lit water allows carbonate platforms to grow on firm foundations, adding broad banks that rise only a few meters below the surface. Other reaches are overwhelmed by sand and mud from the continent, and shelves there are draped with siliciclastic blankets that mute the relief of older surfaces. Between capes, large embayments become sediment traps, and in narrow gulfs, tides and currents can focus energy into channels that cut the shelf and carry material along its edge. Latitude provides a simple map key that divides Pangaea into long climatic and oceanic bands, without yet invoking any later forcing. The equator crosses the supercontinent so low, latitudes receive strong mean solar energy through the year, while high latitudes to the south and north receive less on average and show a larger seasonal range. Because the landmass spans these bands, different limbs of the continent experience different annual rhythms of heating and cooling. The contrast between the thermal inertia of the oceans and the faster response of the land creates pressure gradients that steer broad winds, and the long uninterrupted fetch of Panthalassa allows swell and surface drift to build as they track along the margin. Narrow passages in the Tethys can accelerate flow and create localized jets, while sheltered recesses allow calmer water to persist and collect fine sediment. On land, a patchwork of basins records the slow flexure of the crust and the accumulated weight of sediment. Some depressions began as rifts with steep flanks and deep centers. Others are wide, gentle sags that subside steadily and accept long sequences of deposits. Their margins trap coarse debris from nearby uplands, while finer silt and clay drift toward their centers and settle through quiet water. Evaporitic flats occupy parts of restricted basins where outflow is limited and surface water can concentrate salts, while shallow perennial lakes fill other basins wherein flow balances evaporation and subsurface loss. In the far interior, broad plains hold space for long meandering rivers, while along foothills alluvial fans spread gravel across Piedmont belts. These contrasts in accommodation supply and gradient yield a checkerboard of archives that will later hold fine-scaled records of change. Drainage networks arise from these contrasts in height and slope. Short steep streams descend from mountain belts and deliver cobbles and sand to adjacent forelands. Across the wide interior low-slope trunk, rivers wander by Furcut and rejoin building and branching systems and long floodplains that store fine material between overflows. Through the course of many hundreds to thousands of kilometers, these rivers integrate large areas of the continent and carry their loads toward coastal plains. At some margins, they fan into large deltas that prograde into shelf seas. At others, they enter estuaries where tides and waves sort and redistribute sediment along shore. Where coastlines offer broad accommodation, river mouths can split into multiple distributaries and construct lobes that advance and retreat in response to slow shifts in space and level. Surface materials further reflect the geographic frame. Broad dune fields lie across parts of the interior, where supply of sand is sustained and relief is gentle, while gravel aprons fringe mountain fronts where slopes are steep. Loose-like blankets drape leeward margins of uplands, their fine grains settling from air and building subtle sheets that smooth the landscape. Along coasts, beach ridges and strand lines mark the slow landward or seaward steps of shorelines over long intervals. Farther offshore, contour parallel drifts align with persistent bottom flow, and isolated carbonate mounds rise where the seafloor remains within the lighted zone. In depressions with poor drainage, organic-rich muds can gather, building dark layers that record quiet water and slow accumulation. Sea level relative to the land decides how far the ocean floods the margins and how wide the shallow shelves become. A higher stand expands embayments and pushes shorelines landward along gentle slopes, while a lower stand exposes broad flats and moves the coastline seaward. The late Triassic world in this frame includes shelf seas along parts of the Tethys that are broad and sunlit with room for carbonate builders and for shoal complexes that partition water and collect lime mud. Other reaches show dominance of sand and mud derived from land with tidal inlets, bars and mudflats that reshape as energy and supply vary along the coast. Where shelves are narrow, the transition from river mouth to deep water can be swift, and sediment that escapes the shore face can cascade downslope into canyons and fans. Across Pangaea, soils form on varied parent rocks, and under different drainage conditions, turning weathered minerals into layered profiles that mirror relief and water pathways. On steep slopes, thin stony mantles rest on bedrock and feed coarse sediment to valleys during rare overbank flows. On plains, deeper profiles develop with distinct horizons that signal long periods of surface stability and slow movement of water through the ground. Along low-lying coastal plains, shallow water tables allow glade layers and organic-rich horizons to build where drainage is poor. These quiet accumulations convert local climate and topography into durable markers ready to be read where later exposures reveal their structure and colour. Taken together, the arrangement of supercontinent oceans, mountains, basins, shelves and seafloor sets a strict framework for all surface and near-surface processes. Distances across land dictate how far air and water must travel. Shelf widths and basin shapes govern how the sea meets the land. Upland height and plateau breadth fix how much potential energy is available to move sediment downslope. The presence of long interior plains offers broad spaces where rivers can wander and where sediments can rest and build layered records. Narrow straits and island chains modulate exchanges between basins, focusing currents into jets in some places and allowing calm pooling in others. Against this steady frame, the late Triassic scene takes shape as a map of constraints that guide what follows without yet invoking any later disturbance. The atmosphere over Pangaea stands in a balanced state that reflects the broad geometry of land and sea and the steady receipt of sunlight across latitudes. Large circulation cells carry heat and moisture in predictable bands. A Hadley cell defined as a rising belt of warm air near the equator, and sinking limbs in the subtropics sets the first-order pattern, while mid-latitude westerlies and polar easterlies complete the frame farther from the equator. The intertropical convergence zone, the near-equatorial belt where surface winds meet and air ascends, meanders with the seasons and follows the warmer surface temperatures across the supercontinent and nearby seas. Over the long interior of Pangaea, summers warm quickly and drive low pressure that pulls moist air inward along preferred corridors, and winters cool the land faster than the surrounding oceans, raising surface pressure and weakening inflow. This seasonal breathing of the continent produces monsoon behaviour in simple form, with a summer wet tendency at low to middle latitudes nearest the convergence belt, and a winter dry tendency as subsiding air dominates. The term monsoon here marks a seasonal reversal in low-level winds and a linked change in rainfall, not a single storm style, and in this frame it operates without strong extremes. Greenhouse gases hold the planet in a warm baseline relative to earlier Paleozoic states. Carbon dioxide sits at elevated levels compared with later eras sustained by volcanic outgassing, the weathering of fresh rock on land, and the slow exchange of carbon between oceans and atmosphere. Methane contributes as a trace greenhouse gas from wetland soils and shallow seafloor sources, but its steady removal by oxidation and photochemistry keeps it from building unchecked. Water vapour remains the dominant day-to-day greenhouse component, rising and falling with temperature and circulation, and cloud cover modulates incoming and outgoing radiation across belts and seasons. Aerosols a mix of fine mineral dust from interior deserts, sea salt from breaking waves, and volcanic sulfate from persistent but not extreme activity provide condensation nuclei for clouds and affect how sunlight is scattered or absorbed. Yet their concentrations hover within ranges that the system has long accommodated. Across the supercontinent, the contrast between land and sea organizes pressure gradients that steer winds. Over Panthalassa, sea surface temperatures change slowly, so marine air that moves onto land carries a memory of conditions averaged across broad expanses. Along the Tethyan margins, complex shorelines and island arcs create local eddies and jets that may focus moisture into narrow plumes, but these effects remain regional. Far inland, where air must cross many hundreds to thousands of kilometers of terrain, moisture content declines as water condenses and falls out along the path, leaving drier air to continue toward the continental core. Orographic lifting over uplands forces additional condensation and rain on windward slopes, and allows descending air on leeward sides to warm and dry, producing rain shadow effects that stamp sharp contrasts on neighbouring regions without altering the wider pattern. Seasonal cycles march with regularity. At low latitudes, the annual temperature range is modest, and the main rhythm comes from the northward and southward shift of the rising branch of the Hadley Cell. At mid-latitude, summers are warm, and winters are cool to cold, and the jet streams shift accordingly. Storm tracks follow the westerlies and carry transient disturbances that supply rain along coasts and across the near-interior plains, with the strongest baroclinic contrasts where temperature gradients are tightest. Tropical cyclones may form over warm seas and strike some shores near late summer and early autumn, but their overall frequency and strength sit within a band that the coastlines have long recorded in stratified sand bodies and shoreline scars. The balance between convective storms over land and stratiform rain linked to frontal systems gives each region a characteristic seasonal hydrograph that varies in amplitude with latitude and distance from the sea. Humidity and cloud regimes follow this structure. Over equatorial belts, deep convective towers build on many days and pile anvil clouds that shade broad areas. In the subtropics, subsiding branches of the Hadley Cell maintain clear skies with broken cumulus over land by day and low marine stratocumulus over cooler waters by night and morning. Mid-latitude skies show a variable mix of layered and convective clouds tied to passing disturbances. High thin cirrus trails across many regions and modulates outgoing long-wave radiation without producing rain at the surface. The diurnal cycle over land shows warm afternoons that favour updrafts and scattered showers where moisture is available, and calmer nights that allow fog to gather in basins and river valleys under light winds. None of these behaviours depart from long-held norms for this climatic frame. Baseline surface energy balance supports warm conditions on average. Incoming solar radiation is high near the equator and declines toward the poles, and surface albedo varies with rock-type soil, moisture vegetation cover, and along shelves and shallow banks with the clarity and depth of coastal water. Vegetated belts at low and middle latitudes transpire water that cools leaves and humidifies the boundary layer, while sparsely vegetated or bare regions return a higher fraction of absorbed energy, a sensible heat, strengthening local thermals. Sea breezes and land breezes arise daily along long stretches of coast, organising afternoon storms inland on some days and clearing skies on others. Inland basins with limited outflow respond strongly to heating, and demonstrate large day-night temperature ranges that govern when winds slacken and when dust can loft. The carbon cycle at this stage operates near quasi-steady balance when averaged over long intervals. On land, plants fix carbon during the growing season and return much of it to the air through respiration and decay. Small fractions are buried in soils and in organic rich sediments where conditions allow. In the oceans, plankton take up carbon and carry it into food webs and in part into sinking particles that deliver a slow rain of material to depth. Chemical weathering of silicate rocks consumes carbon dioxide as dissolved ions and bicarbonate travel to the sea, where they help maintain the inventory of dissolved carbon species that buffer changes in acidity. Carbonate minerals precipitate in warm, clear, shallow marine settings and dissolve at depth where dissolved carbon dioxide is higher, closing loops that tie the atmosphere, land and ocean into a shared ledger. Background volcanism returns carbon from the interior, mainly along mid-ocean ridges and arcs, and the sum of inputs and outputs drifts within bounds that the climate system reflects. Dust fluxes supply micronutrients such as iron to parts of the oceans and modify radiation over land. Interior source regions release fine mineral particles during dry, windy periods when soils are exposed and vegetation is sparse. These particles scatter sunlight and can cool the surface slightly beneath hazy skies, while warming layers aloft subtly shifting stability and cloud formation. Over water deposited iron can nudge productivity, where it is otherwise limited, though the effect is regional and modulated by currents and stratification. Salt spray from coasts adds sea salt aerosols that seed clouds and carry halogens that participate in atmospheric chemistry. Together, these background aerosol fields build a textured canvas rather than a disruptive force. Baseline precipitation patterns emerge from this organization. Equatorial and near-equatorial belts receive frequent rains, though the interior reach of those rains into Pangaea varies with season topography and the position of the convergence zone. Subtropical belts remain comparatively dry under persistent subsidence, broken by episodic intrusions of moisture or by mountain-forced lifting. Mid-latitude coasts receive steady frontal precipitation through cool seasons and scattered convective storms in warm seasons. Inland plains see a regime of infrequent but sometimes intense summer storms, balanced by long dry spells with flow paths that connect uplands to distant basins. Evaporation from warm seas replenishes the moisture that these rains draw down, and the cycle repeats with slight drifts tied to slow shifts in sea surface patterns and land surface states. This climatic baseline carries a quiet set of feedbacks that keep swings within limits over long spans. Vegetation cover influences soil moisture and surface reflectivity, which in turn shape local temperature and humidity. Soil moisture buffers daytime heating and supports afternoon clouds. When soils dry, temperatures rise more quickly, and the tendency for moisture import increases, yet without strong external push. The system returns toward its mean. Over shallow shelves, clear water allows high light levels that support carbonate-producing communities, which brightens the surface and slightly increases reflectivity along parts of the margin. Over deeper water cooler surfaces and low clouds maintain a different balance that stabilizes the marine boundary layer. Across these belts, the atmosphere acts as a mediator, moving heat and moisture so that no single region drifts far from the broader pattern for long. In sum, the late Triassic air column above Pangaea holds to a warm and organized state with predictable seasonal wind reversals, steady bands of ascent and descent and rainfall that tracks latitude relief and distance from the sea. The land and the nearby oceans exchange heat and moisture in familiar rhythms, and the carbon, water and energy cycles operate within ranges that long shape the surface. The frame remains stable, the patterns repeat, and the atmosphere carries on its role as a large layered engine that takes sunlight, moves, air condenses water, and returns it to ground in measured paths. Nothing in this moment departs from the steady rule set by geography and by the long-running balance between incoming and outgoing energy that the planet holds. Forcing begins as a quiet tilt in the planet's energy budget, rather than a single sharp break, and it emerges from processes that operate together over many thousands of years. A large igneous province defined as the rapid outpouring of very large volumes of basalt across short geologic intervals grows in the region later known as Rangelia, and repeated eruptive pulses add carbon dioxide, water, vapor, sulfur, dioxide, and halogens to the air. Carbon dioxide is long-lived and traps outgoing infrared energy, raising the downwelling heat that the surface feels by day and night. Water vapor rises as a feedback, because warmer air holds more moisture, which itself strengthens the greenhouse effect. Sulfur dioxide converts to fine sulfate droplets that scatter sunlight and cool the surface for seasons to a few years. But these short episodes sit within longer spans where carbon dioxide remains elevated. Ash falls out more quickly and darkens snow-free surfaces for days to weeks, while adding trace nutrients to soils and sea surfaces downwind. Against this composite background, the net radiative balance nudges warm, and even a small persistent surplus renewed by new eruptive phases is enough to shift the statistics of the air and the water that move through it. The atmosphere does not leap to a new state. It leans. That lean expresses itself through temperature, humidity, and pressure gradients that set up the next steps of change. The air column warms first near the surface, thickening the layer in which convection can rise. Because the capacity of air to hold moisture grows strongly with temperature, evaporation increases over warm seas and moist soils, and the near-surface layer becomes more humid on average. The extra moisture matters not only because it is water that may fall as rain, but because condensation releases latent heat that powers deeper clouds and stronger updrafts, where rising motion is favoured by geography, and the broad circulation storms grow taller and live longer before they rain out. Where sinking motion is common, the same warmer, moister inflow can still seed brief storms when surface heating is strong, raising the odds that a hot afternoon tips into showers that formerly would have failed. The seasonal heartbeat of winds also responds. A monsoon is a seasonal reversal of low-level flow, forced by the contrast in heating between land and ocean. As summers grow slightly warmer over the wide interior of Pangaea, surface pressure falls more deeply inland, and onshore winds strengthen along favoured coasts. Moist marine air penetrates farther across plains and plateaus during the warm season, and upslope winds more often reach the lifting level needed to condense clouds. In the cool season, the land still relaxes toward higher pressure than adjacent seas, but the previous wet months leave soils, moister lakes fuller, and shallow groundwater nearer to the surface, so the next warm season begins from a wetter base state. This memory in the land surface allows later storms to grow earlier in the season and to travel farther along lowlands before drying out. Ocean surfaces follow the forcing with a lag that depends on mixed layer depth and currents. Sunlit layers warm by fractions of a degree over years to decades, increasing vertical stability during warm seasons and reducing the frequency of deep mixing events that would otherwise bring cool, nutrient-rich water upward and push warm surface water downward. The warmer surface loses water to evaporation more readily, which both dries and cools the skin of the sea and humidifies the boundary layer above it. Prevailing winds carry this added moisture toward coasts and then inland along corridors set by relief. Narrow straits and island arcs in the Tethyan realm funnel flow into jets that can concentrate water vapor into elongated plumes, while broad open margins allow moisture to spread in wide fans that water shelf seas and adjacent plains. Dust and other aerosols modulate the path. Fine mineral particles from interior drylands loft more easily when pre-season winds rise, but as rains become more frequent in warm months, they wet surfaces, crust soils, and promote plant cover, which in turn lowers dust emissions later in the season. Fewer dust grains reduce one class of cloud condensation nuclei, yet increased sea salt aerosols along storm-beaten coasts and increased biogenic particles over vegetated belts supply others. The balance of particle types influences droplet size distributions and the brightness of clouds. In some regions, clouds become more reflective and last longer. In others, they more readily produce rain. These microphysical shifts are regional and vary with storm type and air mass history, but together they support a trend toward more frequent precipitation events in settings that were previously close to the edge between wet and dry outcomes. Internal variability rides on top of the forced lean and sets the timing of wet and dry spells. Jet streams meander, high pressure cells drift, and sea surface patterns in marginal basins wax and wane. These modes make one decade wetter and the next less wet in any given place, yet the longer view shows a higher average humidity and a longer warm season in which rain can occur. Closed basin lakes respond by rising more often than they fall, and river stage records show clusters of higher peaks, separated by shorter, dry intervals. The composite result is not a new type of weather, but a changed distribution within familiar types. More days cross the humidity threshold for deep convection in low and middle latitudes. More nights remain warm enough that boundary layers do not fully decouple, allowing morning clouds to build earlier. More weak disturbances survive the crossing from sea to land because surface moisture is abundant and soils are primed to recycle water through evapotranspiration. Orographic effects persist, but the catchments that feed them begin from wetter ground, so upslope rains translate into longer hydrographs rather than single sharp pulses. As the forcing continues, background cloudiness increases in some belts, moderating daytime extremes even as nights remain warm. This slight damping of daily thermal range does not counter the larger moisture gain. Rather, it stabilizes boundary layers against sporadic gusts and allows organized mesoscale systems to travel longer distances along pressure corridors. Over the course of many seasons, small increments accumulate into differences that are clear in the archives that form at the surface. More frequent rains mean more frequent wetting fronts that move through soils and leach soluble ions. Increased evaporation means stronger surface fluxes from open water and irrigated vegetation, which in turn cool local afternoons and feed additional cloud formation downwind. Over warm seas, thin lines of convergence strengthen and mark corridors where showers repeat. Over plains, storm downdrafts lay cool pools that lift moist air at their edges and spawn new cells in arcs that sweep across basins. The large scale holds, yet the statistics within it bend toward higher humidity, more condensed water aloft, and a higher fraction of days with measurable rain in regions already susceptible to monsoon or convective activity. Across all of this, uncertainty remains about the exact share of cause among the contributors. Volcanic carbon dioxide and water vapor are durable and global in their reach. Sulfate haze is short-lived and regional. Halogen chemistry can alter ozone and high-altitude heating in complex ways. Changes in vegetation cover feedback on albedo and roughness. Slow drifts in sea level adjust shelf widths and coastal temperatures by modest amounts. The common ground across records is the sign of the lean and its persistence across many seasons and multiple eruptive phases. The air is warmer on average, the near-surface layer is more humid, and the seasonal pressure contrasts that drive onshore flow are stronger in warm months. With that combination in place, the stage is set for a hydrological cycle that runs faster, with more evaporation, more transport, and more frequent condensation along familiar lines of ascent, all within the rules enforced by the geometry of Pangaea and the steady belts of the global circulation. Air over Pangaea now carries more moisture in its lower layers, and the increase is steady rather than abrupt. Warmer ground and warmer nearby seas lift evaporation by small amounts each day, and the sum across seasons raises the average humidity that moves inland. Moisture in the air is water in vapour form, and the capacity of air to hold this vapour rises quickly with temperature, so the same breeze that once arrived, comparatively dry, now arrives with more invisible water mixed into it. As this air crosses coasts and plains, it loses a little water wherever gentle ascent cools it, to the point where droplets can form, yet the background supply is high enough that the loss is replaced quickly by fresh evaporation and by additional inflow from the sea. The near-surface layer becomes both warmer and moister, a combination that deepens the convective boundary layer on many days and lifts cloud bases to heights where growing towers can tap latent heat released by condensation. That latent heat strengthens updrafts, which allows clouds to grow higher before they rain out, and the cycle repeats as long as surface heating and moisture import continue through the afternoon. Monsoon behaviour grows more pronounced without becoming chaotic. A monsoon is a seasonal reversal of low-level winds caused by land heating and cooling faster than the ocean. During warm months, pressure over the interior falls relative to the sea, and onshore flow strengthens along the margins that connect most directly to the core of Pangaea. Moist marine air penetrates farther inland along these corridors, reaching basins that formerly received little summer rainfall. On approach to uplands, upslope breezes more often reach the lifting level needed to condense clouds, so afternoon showers become more frequent on windward shoulders and their flanking plains. When the season turns cool, surface pressure over land rises again, yet the prior months leave soils, wetter lakes fuller, and shallow groundwater closer to the surface, so the next warm season begins from a moister base state that helps early storms form with less delay. This seasonal memory is not a new force, it is simply water retained in the landscape that the atmosphere can draw upon when heating resumes. Moisture transport takes recognizable shapes. Narrow plumes arise where straits and island arcs in the Tethyan realm focus low-level flow, creating filaments of high humidity that arc onto nearby coasts and then curve inland along valleys. Broad fans form along open margins where winds enjoy long fetch over warm water and can spread vapour evenly along shore before the air turns toward the interior. Once ashore, these plumes and fans are steered by relief and by the low-level pressure field into corridors of convergence where clouds cluster and showers repeat. At the scale of a day, lines of showers march along outflow boundaries left by prior cells, and gentle low-level jets guide nocturnal clusters that ride with the pressure gradient. At the scale of a season, the preferred corridors appear and fade with the slow drift of the continent's thermal low and the position of the near equatorial belt of ascent, so one region receives a string of wet weeks, while another waits under broken sky until the belt shifts. Cloud fields reveal the higher moisture with clarity. Shallow cumulus still mark fair days, but the depth to which they can grow increases, and taller forms become common in the warm season where vapour is abundant. Spreading anvils from mature storms cast broad shields that soften afternoon heating beneath them, without stopping convection entirely because inflow air stays humid and recovery between downdrafts is quick. Mid-level layers formed by gentle ascent ahead of weak disturbances appear more often and drizzle more readily. High thin ice clouds trail downwind of large towers and slow the loss of heat to space during the night, nudging the surface toward warmer minima that keep the boundary layer partly coupled until morning. Under these canopies, early day convection can begin with less delay once the sun rises, so afternoon peaks arrive sooner and last longer into evening. Microphysics responds to the altered aerosol mix. Fine mineral dust from interior source regions declines during wetter months as more frequent wetting stabilizes surfaces. Plant cover expands and crusts form on exposed soils. Sea salt increases along stormy coasts, where breaking waves fill the marine boundary layer with salt-rich particles, and organic particles from forests and wetlands become more common as vegetation cover and humidity rise. The balance of particle types influences initial droplet sizes and the brightness of clouds. With fewer very fine dust particles, some clouds form with slightly larger initial droplets and convert water to rain more efficiently, which favours warm rain in shallow clouds that would once have remained non-precipitating. With more sea salt and organic nuclei, other clouds sustain numerous small droplets that reflect more sunlight and live long enough to merge into broader canopies before raining. The result varies by region and storm type, but in many places the outcome is a higher fraction of days with measurable precipitation from systems that earlier would have dissipated before coalescence began. The daily rhythm adjusts in step. Overland afternoons remain the prime hours for storm initiation, yet the clock shifts earlier, where morning humidity is higher and where the previous night leaves shallow cloud ready to deepen. Outflows from one storm often seed the next by laying a cool pool whose advancing edge lifts warm, moist air just enough to trigger new updrafts. This relay can carry a chain of cells across wide basins. Nights stay warmer under broken high clouds, so boundary layers decouple less completely, and shallow eddies persist that can support light showers near dawn when gentle convergence gathers along valley floors. Over shelves and coastal plains land breezes in the small hours, and sea breezes after midday continue their familiar cycle. But the sea breeze front carries more moisture inland and more often ignites lines of storms where it meets downslope flow or prior outflow pools. Regional contrasts remain anchored by latitude and relief. Subtropical belts under persistent subsidence still show long dry stretches, yet coastal strips within them receive more frequent intrusions of humidity that occasionally break the pattern with showers and short-lived storms. Mid-latitude coasts tied to the westerlies see more precipitation on average during the cool season, as moist air masses meet rising terrain with the added water vapour, allowing fronts to lay wider swathes of stratiform rain behind them. Near the equator, the near-stationary belt of ascent supports frequent convection, and its seasonal migration spreads the influence across adjacent belts for longer intervals than before. Far interiors remain less wet than coasts, but the reach of moist days extends deeper into the continent, so rivers and closed basins register more frequent rises. Hydrology in the air links back to exchanges with the surface. Evaporation from lakes, marshes, soils and plant canopies increases, and much of that moisture returns locally as afternoon showers that fall on the same watersheds. This recycling tightens water budgets and maintains soil moisture between larger events. Where open water is, extensive bands of warm season showers form downwind under gentle temperature contrasts. Where forests expand into formerly open ground, roughness and transpiration together deepen the daytime boundary layer and provide a steady source of vapour that feeds nearby clouds. Gentle feedbacks reinforce the pattern without pushing it beyond familiar bounds. As soils stay wetter, daytime sensible heat flux declines relative to latent heat flux, which keeps near-surface temperatures a little lower during peaks and slows the onset of desiccating downslope winds. As canopies densify in humid belts, shade reduces evaporation from the ground, while leaf surfaces continue to transpire, shifting where water returns to the air but not its total. As clouds become more frequent, daytime sunlight at the ground softens slightly, while nights gain a little warmth under thin ice canopies, further narrowing the daily temperature range that the boundary layer must traverse to trigger convection. Through all of this, uncertainties in the exact share of cores among volcanic gases, slow circulation shifts and surface feedbacks remain, yet the shared signal across landscapes holds. Air near the surface holds more water on average. Moist inflow reaches farther inland during warm months. Weak disturbances and gentle upslope breezes more often grow into clouds that live long enough to rain. Dry periods still occur, and some basins remain in the lee of mountains that wring out inflow before it reaches them. But the odds have moved toward more frequent condensation along familiar lines of ascent. The atmosphere's role has not changed. It still takes water from warm surfaces, carries it along. Pressure corridors condenses it where lifting is present and returns it to ground in measured paths. What changes is the background amount of water available to move through those paths, and with that change the cadence of clouds and rain adjusts toward a wetter warm season across wide tracts of the supercontinent. Surface oceans around Pangaea respond first in the sunlit mixed layer, the shallow upper band of water that stirs with winds and waves and communicates directly with the air. As the atmosphere warms and holds more moisture, evaporation and heat exchange change the balance at the sea surface by small amounts each day, and the accumulation of those increments over seasons nudges the mixed layer towards slightly higher temperatures. A warmer mixed layer becomes more stratified because the density contrast between warm surface water and cooler subsurface water increases, and this contrast reduces the depth to which wind can mix momentum and cool the surface on ordinary days. The result is a shallower layer that warms sooner in each season and stays warm longer into autumn, while ordinary wind events no longer overturn it as easily. At the same time, more frequent rains and stronger runoff from nearby land deliver fresh water to coasts and shelves, and this fresh water caps the sea surface in lenses that ride above saltier water. These low-density lenses spread along shorelines and across shallow banks, sharpening the vertical gradient in density and further resisting mixing. Where rivers meet the sea, plumes of brown and green water expand and thin as they travel, carrying fine sediment and dissolved ions from the land. The junction between plumes and clear shelf water becomes a shifting front, whose position changes with winds and tides, and along this front the contrast in density and clarity sets where light penetrates and where it fades quickly. Light in the upper ocean sets the thickness of the photic zone, the layer in which photosynthetic organisms can grow. In clear offshore water, light penetrates deeply, and the photic zone may extend tens of meters, but along shelves under the influence of plumes and resuspended sediment, the photic zone shoals. Rain fallen on land and delivered by rivers carries clay and silt that scatter light, and storm waves and tidal currents lift older mud from the seafloor into suspension. The combined effect is a slight dimming of shelf waters during wet seasons, strongest near river mouths and weakest on outer banks where clarity can persist. This dimming matters for carbonate platforms' broad, shallow banks, where organisms produce calcium carbonate that accumulates as muds, sands and bound frameworks. These platforms rely on sunlit water, stable salinity and low concentrations of fine sediment that would otherwise clog pores and smother surfaces. During wetter intervals, the shoreward sides of platforms receive more frequent pulses of fresh and turbid water and spend longer periods under light-limiting conditions. Clear offshore faces remain brighter, yet even there the shallower mixed layer warms more quickly and changes how waves and currents distribute heat and particles across the bank. Carbon chemistry in the mixed layer shifts in ways that stress carbonate precipitation. Carbon dioxide dissolves into the upper ocean and forms carbonic acid that dissociates into bicarbonate and hydrogen ions. The added hydrogen ions reduce the concentration of carbonate ions that combine with calcium to form solid carbonate minerals. The measure that captures the ability of seawater to support carbonate mineral formation is the saturation state, which is high when carbonate ion is abundant and lower when it is scarce. Warming raises saturation by favouring precipitation in purely thermal terms, yet the addition of carbon dioxide pushes in the opposite direction by drawing down carbonate ion, and the freshening by river input reduces alkalinity and further lowers saturation near coasts. The net effect in many shelf settings is a modest reduction in saturation from prior levels, most marked nearest to river plumes and weakest on outer shelves and banks. In turn, organisms that build skeletons and shells from carbonate experience higher energetic costs to maintain growth, and communities on the inner flanks of platforms become more vulnerable to disturbances that interrupt their calcifying work. Hydrodynamics over platforms also changes as the mixed layer shoals and freshwater lenses appear. A thinner warm layer responds more quickly to wind, so short wind bursts can create sharper surface jets and stronger shear across the thermocline. These jets carry warm, sometimes slightly fresher water across bank tops, while the shear promotes small-scale turbulence that stirs particles without fully mixing the column. On stormy days, waves grow over long fetches and push water up the gentle slopes of banks, then draw it back in pulses that ventilate shallow depressions with surface water. Between storms, tidal currents sort sediments along predictable corridors, leaving bands of well-winnowed sand where flow accelerates and pockets of mud where it slows. In wetter intervals, the balance shifts toward finer material in many inner shelf settings, and the bank tops see more frequent episodes in which visibility drops and particles settle slowly into crevices. The physical template keeps its familiar shapes, but more hours per season feature turbid water and freshened caps that complicate the growth of carbonate producers near shore. The sources of sediment arriving on shelves shift as continents weather and rivers swell, yet the surface expression is simple. Plumes bring higher loads of clay and silt that flocculate in brackish water and fall out near estuaries, building deltas and subaqueous lobes that push the coastline seaward in places. Farther from river mouths, finer particles stay aloft long enough to spread across broad areas and settle as thin drapes during calm spells. On bank margins, these drapes blur older ripple fields and fill voids between skeletal grains. Sands and gravels still move under fair weather currents and storms, but they do so in company with more fines that cloud the water whenever flow increases. The outcome is a shelf that spends more time in a lightly hazy state, and less time in the clear high contrast light that best supports widespread carbonate production on inner margins. Where clarity remains high on outer platforms, production continues but faces the chemical push against saturation, just as on the interior, so net accumulation declines slightly, even where light is plentiful. Biological communities in the photic zone track these physical and chemical shifts without requiring any new forms or behaviours. On open shelves and outer banks, planktonic producers benefit from a longer warm season and steady stratification that keeps them in light, and episodic inputs of river-borne nutrients support short pulses of growth where fronts focus mixing. On inner shelves, turbid periods and lower saturation favour communities that tolerate variable salinity and light, and that can trap and bind sediment rather than build rigid frameworks in all settings. The combined effect across many margins is a reduction in the dominance of clear water carbonate factories along inner and middle shelves, and a greater share of mixed carbonate and siliciclastic sediments that record both biological production and delivery from land. Outer ramps and bank crests remain sites of carbonate sand production and transport, yet the pathways that carry those sands landward into protected lagoons lengthen and narrow as turbid barriers persist more often across passes. Storm climatology at the sea surface also matters because waves and surges reset platform surfaces and redistribute sediments. With a warmer atmosphere carrying more water vapor, storms can draw on higher moist static energy and produce broader rainfields, yet their winds over water vary with larger circulation features that remain within familiar bounds. In many sectors of the Tethyan margins and sheltered Panthalassan embayments, the outcome is similar wave energy, but more frequent rain bands that freshen and darken the upper centimetres of the sea. Repeated wetting and reduced light during stormy weeks limit daily photosynthetic work on inner shelves, and recovery between events is shorter when evaporation and runoff maintain fresher lenses. Post-storm fair weather still brings clear days, and carbonate producers still grow, yet the seasonal total of days with optimal light and salinity declines, and the sedimentary record shifts to include more layers of fine material interbedded with carbonate muds and sands. Shelf morphology mediates all these responses. Where margins offer wide, shallow platforms with gentle slopes, freshened lenses spread slowly and linger after rains, extending the duration of light limitation. Where margins are narrow and drop quickly into deep water, river plumes hug the coast and plunge off the shelf during strong winds, which limits their time over bank tops but sends their finer load along the slope. Islands and microcontinents create lee zones where clear water can persist even during wet months, and these refuges continue to host bright sand shoals and skeletal banks that feed longshore transport belts. Narrow straits accelerate exchange and can reintroduce clear oceanic water onto shelves during some tidal phases, briefly improving clarity on bank interiors before the next surge of runoff arrives. The patchwork that results is spatially complex at scales from headland to headland, yet coherent when viewed across regions, a general tilt toward more frequent freshening and turbidity near land, a small chemical push against carbonate saturation, and a modest reduction in net carbonate accumulation across inner to middle shelves. Archives that form in the uppermost layers of the sea record the sum of these changes. Laminated muds build in embayments where plumes slow and spread, each pair of light and dark laminae marking shifts between fair and wet conditions. Macritic layers on bank tops show more frequent thin interbeds of silt and clay, and oolitic shoals display breaks where accretion pauses under reduced light or freshened caps. Skeletal sands carry a higher share of fragments reworked from older beds as new growth struggles during turbid stretches. On outer ramps, cross-bedded carbonate sands persist, but thin, slightly reflecting both chemistry and the shorter pathways that now deliver sands into back barrier settings. None of these signals require a wholesale change in circulation or storminess at the surface. They follow directly from the warmer, more humid air, the stronger delivery of fresh water and fines to the sea, and the gentle chemical shift in carbon species that accompanies a higher reservoir of carbon dioxide above the waves. Below the bright mixed layer, the ocean interior adjusts to a surface that is warmer, slightly fresher, and more stably stratified. The thermocline, the depth band where temperature changes quickly with depth, strengthens and shoals, and the pycnocline, the density gradient itself, aligns with it. so that ordinary winds no longer push oxygen-rich surface water as deeply as before. Less frequent deep overturning means that interior waters exchange with the air more slowly. Oxygen, the most direct tracer of this balance, shows the first clear response. At the surface, contact with the air and photosynthesis by plankton replenish oxygen. Below, the light microbes respire sinking organic particles and use oxygen in the process. When supply from above declines while demand below persists, the minimum in dissolved oxygen thickens and spreads. Along wide shelves and inside semi-enclosed Tethyan subbasins, the oxygen minimum zone grows downward into deeper water and upward into layers that once remained well ventilated, while in the open interior it broadens along the paths set by intermediate density surfaces, where oxygen falls to very low values for long enough. The near seafloor community that normally churns mud and sands retreats, and fine laminae accumulate with little disturbance until renewal events arrive. Chemistry follows a familiar sequence as oxygen declines. In fully oxygenated water, microbes use oxygen to oxidize organic matter. When oxygen is scarce, they turn to nitrate, then to manganese and iron oxides, and in the most restricted pockets to sulfate. Denitrification removes fixed nitrogen by converting nitrate to nitrogen gases that are vented when waters return to the surface, and this can lower the local nitrogen inventory that upwelling would otherwise supply. Reduction of manganese and iron releases those metals to the dissolved phase, and as the water later meets oxygenated layers, they reprecipitate as thin bands of oxides that streak the sediment with dark and reddish tones. Where sulfate reduction proceeds in poor waters beneath low oxygen, bottom water iron, sulfide minerals such as pyrite form, often as tiny framboids that indicate water masses that remained very low in oxygen. Carbon species in the interior shift along with redox. Respiration increases dissolved inorganic carbon at depth and raises acidity, while the slower delivery of oxygenated waters allows these changes to accumulate between renewal pulses. The saturation state for calcium carbonate declines in interior waters, and the depth at which carbonate grains dissolve more rapidly, often marked later as a sharp change in carbonate content of sediments, tends to shoal by small but repeated increments in basins that experience strong remineralization. Surface productivity, which sets the flux of sinking material, helps control how far these chemical changes go. Near river mouths, increased delivery of phosphorus and silica supports blooms when light is adequate, and their remains sink into the upper part of the oxygen minimum zone, where they are remineralized and drive oxygen even lower. Offshore steady stratification holds plankton in light and favors continuous moderate production. Storms and frontal intrusions intermittently deepen the mixed layer and deliver oxygen and nutrients downward, and these pulses appear in the interior as thin tongues of fresher, cooler, more oxygenated water that slide along density surfaces. Water mass renewal depends on sills and gateways. Many late Triassic marginal basins are separated from the open ocean by narrow straits with shallow thresholds. During cool seasons, dense shelf water can form and spill across these sills to ventilate the interior. As warming and freshening progress, shelf waters reach lower maximum density, and fewer parcels clear the threshold. Where gateways are broad and deep, renewal continues more often, and the oxygen minimum remains thinner and deeper. Where gateways are narrow, renewal is sporadic, and the minimum thickens and touches the bottom more frequently. Trace nutrients respond to the redox backdrop in ways that alter the surface after the interior water returns. Under oxygenated conditions, phosphate tends to adsorb onto iron oxides and settle. Under low oxygen conditions where iron is reduced, phosphate is released to the water column and can accumulate within the oxygen minimum. When that water later upwells or mixes into the surface, the extra phosphate can support productivity and close a gentle feedback that helps maintain the oxygen minimum at the margins. Biology in the interior adjusts without implying sudden innovation. Zooplankton that migrate daily between surface and depth compress their vertical range to avoid the core of the oxygen minimum, and their predators shift with them. Benthic animals on slopes and basin floors retreat to burrowed refuges near seeps or small currents that leak oxygen along the bottom, and where oxygen remains low for long seasons, their tracks fade from the mud. Microbial communities in the upper few centimetres of sediment diversify their pathways for breaking down organic matter and leave layered byproducts that match the order in which electron acceptors are used. The sea floor preserves the net outcome with quiet clarity. In settings where oxygen varies seasonally, thin laminated beds alternate with lightly mixed layers that show traces of burrows. In more persistent dysoxia, laminations stack for longer intervals, and framboidal pyrite becomes common. These laminae register not only low oxygen, but also the pacing of renewal with sharp contacts, where cooler, denser intrusions briefly restored oxidation before the next quiescent spell. Along inner ramps and at the toes of deltas, clay-rich layers thicken during wet years, when particle flux from land is high, and these layers blanket older ripples and mute small bed forms built during clearer intervals. On outer slopes, fine carbonate fragments appear less often, where the depth of rapid dissolution has moved upward and mixed layers show higher proportions of silts delivered from above. Across the interior, the physical pattern stays orderly. The thermocline and pycnocline act as sliding planes that guide lateral movement while resisting vertical exchange. Internal waves and eddies continue to move energy along these planes and to wrinkle the boundaries between water masses, yet the average position of the boundaries holds closer to the surface, and the reach of ventilation events is shallower than before. The chemistry then follows those boundaries with oxygen highest above lowest, in the core of the minimum, and rising again toward deep water that still retains traces of older ventilation, where gateways remain open. In this way, the ocean interior carries the imprint of a hydrological cycle that runs faster at the surface and of a carbon cycle that supplies a steady rain of particles to depth. The result is a layered water column in which renewal arrives. Less deeply, respiration consumes oxygen more persistently in mid-depths, and dissolved inorganic carbon accumulates between intrusions, while seafloor archives keep a clean ledger of laminae pyrite formed in pore waters and small enrichments of elements that prefer low oxygen. The signals vary by basin and margin, because sill shelves and river mouths differ in shape and position, yet the direction is the same wherever stratification is stronger and runoff and rain are more frequent. Continental weathering engages wherever rain meets rock, and in this wetter, late Triassic world the meeting is more frequent and lasts longer each warm season, so the slow conversion of bedrock to soil and dissolved load increases across wide tracts of Pangaea. Weathering means the breakdown of rock into smaller particles and dissolved ions by chemical reactions and by physical processes such as expansion, contraction, and abrasion. Chemical weathering strengthens when water is abundant and warm because reactions that dissolve minerals and alter them into clays proceed faster when thin films of water persist on grains and when percolating fronts move regularly through soil. Primary silicate minerals such as feldspar and pyroxene release calcium, sodium, potassium, and magnesium as they break down, and those cations pair with bicarbonate, a dissolved form of carbon, to travel in rivers toward the sea. The solid residue leans towards secondary clay minerals such as kaolinite under strong leaching, and towards smectite and mixed layers under more moderate leaching, and these clays in turn control how soils hold water and how slopes behave during storms. On steep hill slopes, the increased frequency of wetting weakens near-surface layers and promotes shallow slips that deliver pulses of coarse debris to valley bottoms. On gentle hills, the same wetting deepens, weathering profiles thickens saprolite, the soft rotten rock that underlies many soils and pushes the boundary between fresh and altered rock steadily downward. Where bedrock is carbonate rain, slightly acidified by dissolved carbon dioxide, dissolves meteorite and spare along fractures and bedding planes, enlarging conduits and creating karst features that route water underground and feed springs downslope. The net result is a continent with thicker soil mantles in many humid belts, more frequent small failures on steep flanks and more efficient transfer of dissolved load from uplands to channels. Erosion links these changes to sediment routing. Erosion is the removal and transport of weathered material from where it forms to where it is stored. As storms become more common in warm months, raindrop impact and overland flow mobilize more fine material on bare patches and on cultivated surfaces of that time, and through rills and small gullies, this load finds channels more often. On vegetated slopes, root networks anchor the ground, but also help produce macropores that speed infiltration, which can stabilize surfaces under light rain, yet prime deeper layers to fail under intense bursts when pore pressures rise. Along foot slopes, colluvial aprons, the accumulations of slope waste grow and are reworked by sheet floods that sweep across the base of slopes, carrying a mix of new rock fragments and older soil aggregates toward trunk streams. Boulder and cobble movement remains tied to rare high-energy events, but sand and silt travel in suspension on many more days each year and visit floodplains more often, where they deposit thin sheets during overbank flows and then are picked up again on the next rise. The architecture of drainage networks matters for how far and how fast these materials move. Headwater channels incise into fresh rock, where relief is high, scouring during floods, and building step pools that trap coarse material until the next rise pries it loose. Mid-catchment reaches develop meanders and bars where slope declines, and sediment input is high, and these elements adjust to carry the increased load without abandoning their planform. Farther downstream, broad trunk rivers integrate the response over many source areas and spread floods onto wide floodplains that store fine layers between events. Because wet seasons begin earlier and last longer, flood hydrographs show more modest peaks, repeated over longer intervals rather than isolated extreme crests, and this favours the slow infill of back swamps, oxbows and abandoned channels with clay and organic-rich mud. In this way, the routing system shifts toward greater throughput of dissolved load and suspended fines, and toward longer residence of water in floodplain storage elements that exchange with the active channel during each rise and fall. Rock type or lithology sets local variation within this wider pattern. Regions rich in volcanic lastics and basaltic bedrock weather rapidly under warm wet conditions, and release high loads of dissolved cations that travel as bicarbonate and help buffer river acidity. Regions dominated by quartz-rich sandstones contribute mainly durable sand grains that move during high flows and build bars and sheets, while their dissolved load remains low. Granitic terrains yield abundant kaolinite under strong leaching and deliver both clay and dissolved silica downstream, which influences how channels and wetlands behave when clays flocculate in still water. Carbonate platforms exposed on land release dissolved calcium and bicarbonate directly when rains persist. and the solution cavities they produce focus groundwater toward discrete springs that add steady base flow to streams during the dry shoulder seasons. The mineral mix matters for how deltas later build and for how shelf waters respond chemically, but in this section the focus remains on the land-to-channel step, where enhanced weathering translates into enhanced export. Land surface conditions add feedbacks that regulate how far weathering accelerates. As soils deepen and remain moist longer, plant communities thicken in many belts, and the added canopy shades, the ground keeps surface temperatures lower during afternoons and reduces direct raindrop impact, which together moderates surface wash. At the same time, deeper roots and organic acids from litter and microbes promote mineral dissolution, at depth expanding the zone where cations are stripped from grains and carried into percolating water. In catchments with poor drainage, the water table rises seasonally into the root zone, and reducing conditions develop in lower soil horizons that mobilize iron and manganese. These ions move and precipitate lower downslope painting layers with mottles that record the path of water. In well-drained uplands, repeated wetting and drying expand and shrink clays, which opens and closes cracks that later serve as pathways for fast flow during storms, allowing rainfall to reach channels not only across the surface, but also through short-lived subsurface pipes. Over many seasons, these pathways carve a finer network of preferred routes that guide water and fine sediment downslope. Volcanic inputs during active phases play a supporting role. Fine ash that falls on land dissolves quickly in warm, wet soils, releasing soluble potassium, phosphorus, and silica that stimulate plant growth and alter soil chemistry. In thin layers, the ash weathers to clay and adds to the water-holding capacity of surface horizons. In thicker pockets, it forms perched aquifers that shed water laterally onto slopes and into channels during wet spells. On carbonate-poor uplands, ash-derived alkalis help neutralize soil waters and increase the mobility of some trace elements, leaving subtle fingerprints later recognized in sediment layers downstream. The routing of water and sediment from source to sink can be traced through storage elements that fill and empty as seasons progress. Hill-slope hollows collect colluvium until a threshold is reached, then fail and send loads into headwater channels. Floodplains act as both conveyor and store, with point bars growing during one set of flows and being cannibalized during another. Natural levees slowly build along channel margins and break during crevasse events that deliver fresh pulses of silt into back swamps. Alluvial fans at mountain fronts pulse forward during sequences of wet seasons, their surfaces are vulsing into new courses that distribute gravel and sand across Piedmont belts. Through all of these steps, the median grain size in transport at any one place reflects the balance between local slope water discharge and supply. But the regional trend under wetter conditions is a higher share of fine suspended load relative to bed load, which allows material to travel farther and reach broader floodplain areas before settling. Dissolved load follows every path and leaves the most consistent mark. Rivers carry bicarbonate paired with calcium, magnesium, sodium and potassium toward the sea, and in wetlands along the way, part of the load precipitates as carbonate, where evaporation is strong or where plants draw down carbon dioxide during the day. In well-oxygenated reaches, iron and manganese that entered solution upslope precipitate as coatings on grains. In reducing backwaters, they remain dissolved and move on. The total export of dissolved material increases with each additional wet month, and the reach of rivers widens as base flows rise, and minor channels that once dried each dry season now retain water longer. These changes do not require new river styles. They are extensions of ordinary behavior under a climate that supplies more frequent pulses and sustains higher soil moisture between them. The geological ledger that these processes keep is simple and cumulative. Soils thicken and show stronger leaching profiles in humid belts. Colluvial wedges at the bases of slopes contain more interbeds of fine material deposited by sheet floods. Alluvial fills in valleys record repeated overbank events with closely spaced couplets of silt and clay, and paleo-channels step laterally more often as banks fail after long wet spells. Cosmogenic nuclide inventories in surface grains, if one could read them here, would register faster turnover from bedrock to channel, yet the landscape retains its structure. Mountains shed, Piedmont's spread rivers weave and plains store. Under the 2 million year tilt toward wetter, warm seasons, the continent's weathering engine runs faster. The paths of removal and delivery carry a larger share of dissolved and fine load, and the sediment routed toward coasts sets the stage for how nearby basins will respond when this increased export arrives at their thresholds. Lakes, rivers and deltas act as quiet recorders of wetter seasons, because each stores sediment in ways that encode the frequency, size and timing of flows that enter them. A lake is a standing body of fresh or brackish water that collects runoff from a defined catchment. A river is a moving thread of water that carries dissolved ions and sediment from uplands to lowlands. A delta is the wedge of sediment that builds where a river meets a standing body of water and slows. In a warmer and wetter, late Triassic closed and open, lakes expand across subsiding basins and into montane depressions, and their shorelines step outward across low gradients that offer broad accommodation space for nearshore sands and muds. High stands defined as intervals when lake level sits high, for long spans leave beach ridge sets, wave-cut benches and nearshore bars that stack landward to mark the run of wet years. Low stands leave erosional notches, exposed mudflats and reworked shore-face packages that speak to drying phases that interrupt but do not overturn the long wet tendency. In deeper parts of lakes where bottom waters remain quiet, thinly laminated sediments accumulate as couplets of light and dark layers. When the couplets reflect seasonal changes in supply, they're called varves, and each pair stands for 1 year a lighter, often silt-rich layer from spring and summer inflow, when runoff is strong, followed by a darker, finer, more organic rich layer from calmer autumn and winter deposition. During wetter, warm seasons, the light layers thicken, the grain size shifts slightly coarser, and flood couplets appear within the warm half of the year as sharp-based fining upward beds that repeat every few years. Delta front turbidites, the quiet underwater flows that move along the lake bed when floods plunge at river mouths, lay thin sand and silt sheets that form packets marking clusters of high inflow seasons. Near the margins, shallow sub-littoral zones host wave ripples and small crossbeds that grow during windy periods when water stands high, and these features step upward through time as the lake expands and transgresses onto lowlands during a sequence of wet years. Carbonate precipitates occur in some lakes as shoreline tufers and macritic muds, when evaporation lifts alkalinity and plants draw down carbon dioxide during daytime, yet in a wetter regime dilution by runoff and higher suspended load reduce these precipitates in many basins and replace them with siliciclastic muds that better preserve lamination. Rivers register the same wetness through geometry and grain. Channel belt width increases as bankful discharge rises during longer wet seasons, and meander wavelengths lengthen on low gradients, where cohesive banks can resist erosion until a threshold is passed. Point bar deposits, the arcuate sand bodies built on inner bends, thicken and show more numerous lateral accretion surfaces that dip gently toward the Thaleweg, the deepest path in the channel. Overbank fines on floodplains stack in closer spaced sheets with fewer soil horizons between them, because floods revisit the plain more often and leave thinner pauses for pedogenic alteration. Crevasse splays, the fan-shaped deposits that spread from breaches in natural levees during high stages, become common, and their sharp-based upward fining bodies give a measure of the frequency with which rivers overtop their banks. Avulsions are shifts in channel course, when aggrading beds reach a height that prompts the flow to seek a new path occur, more often on broad plains, where sediment supply keeps pace with subsidence, and the resulting mosaic of abandoned channels and fresh belts spreads laterally to fill the space. Where gradient is higher, braided reaches respond by increasing bar turnover rate, and by exporting a larger share of sand downstream. Yet even there, the suspended load of silt and clay rises relative to the bed load, so floodplain splays grow while gravel sheets remain tied to peak events. Paleohydraulic indicators, simple measures that link preserved forms to flow, mark the change. The median size of crossbed sets increases slightly where floods run higher. Ripple crest spacing broadens in sand-dominated reaches, and scour-fill structures in channel bases deepen and widen as peak flows carve and refill deeper pockets. Wood fragments, if preserved, orient more consistently with trunk flow during longer floods, and align in channel lag deposits that settle as waters wane. In many valleys, the ratio of channel area to floodplain area declines as floodplains grow thicker, records of overbank silt and clay indicating greater time underwater and greater residence of fine material on the plain between flows. Deltas at lake and sea margins hold the clearest pictures of sustained wet seasons because they translate discharge and sediment load into shape. A delta grows by building mouth bars, low ridges of sand and silt that form where river jets decelerate upon entering standing water. As discharge increases and fine load rises, mouth bars prograde faster and split distributary channels, more often creating a branching network that spreads the load across a wide front. Progradation means seaward or lakeward advance of the shoreline through sediment build-out, and it leaves cliniforms gently to steeply dipping beds whose foresets tilt toward the basin and whose topsets are flat or near flat. During a wetter regime, progradation picks up pace, and coarsening upward successions, in which fine material at the base passes upward into sand, as the delta front advances over a point, become thicker and more frequent in the core of lobes. Because floods are more frequent, the tops of mouth bars rework more often, and wave ripple lamination alternates with current ripple forms in quick succession. Freshwater flushing through distributaries increases the buoyancy contrast with lake or marine water and can drive hyperpycnal flows, dense underflows that carry sediment along the bottom when river discharge is very muddy. These leave thin, sandy tongues beyond delta fronts that interleave with quieter silt drapes. Avulsions at the delta plane scale shift the locus of deposition from one lobe to another when channels backfill and spill into lower roots. In wetter phases, the avulsion frequency rises and the delta builds a quilt of overlapping lobes that each carry their own coarsening upward motif capped by marsh and floodplain fines. At the edges, wave and current reworking remains active and rounds, sand into shoreface sheets, but increased fine supply often builds thicker mud belts that damp wave energy and allow vegetation on the delta plane to trap more silt between distributaries. Strand plane segments, the beach ridge sets that parallel a stable to gently advancing shoreline, give way in places to more labat fingered forms that point basinward and speak to stronger river control. In confined embayments where a delta fills space bounded by headlands or structural highs, the shoreline advances rapidly during wet decades, and brackish to freshwater transitions migrate seaward as the delta front passes. In open coasts, the same signal spreads laterally as multiple small lobes advance along shore, and link into a serrated belt of mouth bars and levered channels. Lake deltas show similar behavior at smaller scales and respond tightly to lake level. During high stands, distributary channels split and deliver load to deeper points farther from the former shore, and facets grow steeper in places where plunging flows streak down the front. During shorter low stands within the wet tilt channels incise slightly into topsets, and cut and fill cycles mark temporary retreats before the next wet sequence resumes advance. Flood-dominated deltas where river energy outweighs waves and tides leave the sharpest lobes and the clearest crevasse splay networks, while wave-influenced deltas smear lobes into smoother arcs with sandier shore faces. Both expand faster under wetter supply, but the flood-dominated class carries more mud farther and records more frequent avulsions. Estuarine entrances at some marine margins record pulses of suspended sediment during wet seasons as turbidity maximum zones, the places where landward and seaward currents balance and hold fine particles in suspension. Under more frequent floods, these zones expand and migrate, leaving thicker muddy successions with shell-rich partings where flow weakens seasonally. Tidal channels adjust cross-sectional area to carry the added fine load, and point bars within them fine upward more rapidly as slack water intervals trap clay flakes that flocculate and settle. In freshwater deltas, plant-bound marshes spread as overbank flooding becomes more common, and their peaty mats build faster, yet even these mats are interleaved with silt layers that tie them to frequent crevasse events. The archival value of these systems comes from their habit of storing detailed, repetitive signals tied to hydrology. In lakes, verves and flood couplets yield year-to-decade scale patterns of wetness and calm, and abrupt coarsening show when catchments delivered strong pulses. In rivers, lateral accretion packages and crevasse splays counter avulsions and flood frequency, while overbank sheets close the gaps between events and point to sustained high base flow. In deltas, stacked coarsening upward units, lobate planforms and avulsion-bound sequences measure how often the sediment conveyor shifted its mouth and how quickly the shoreline advanced. In all these settings, the late Triassic tilt toward more frequent rains moves the statistics without erasing the familiar forms. Lakes stand higher more often and lay thicker, light layers in warm season couplets. Rivers fill their plains with closer spaced flood sheets and shift course more often as aggradation keeps pace with subsidence. Deltas prograde faster, split their channels more frequently, and store broader quilts of lobes that overlap and climb. The signals are clearest where accommodation is ample and subsidence steady, because there the beds stack without being eroded during lean spells. Where space is limited, the same tendencies still appear in cut and fill cycles and in channel geometries that widen and shorten their bends. The sum is an expanded library of water-written records that hold the cadence of a wetter, warm season world in the exact order and scale of the flows that made them. Soils record the balance between water supply, evaporation and drainage, and in a warm late Triassic interval with more frequent rains, they build features that catalogue humidity at ground level with quiet precision. A soil begins as weathered rock and organic matter arranged into horizons that differ in colour, structure, grain size and chemistry. As wet seasons lengthen, percolating water moves farther and lingers longer in the profile, and that extra residence time drives leaching redox reactions and clay movement that leave durable traces. Colours mute from bright reds toward duller greys and greens, where iron shifts between oxidized and reduced states under fluctuating water tables. Mottles the irregular patches of contrasting colour bloom where oxygen comes and goes with each rise and fall of groundwater, Clay skins, thin films of aligned clay that coat pore walls and ped faces, accumulate where fine particles move downward in suspension and then stick along flow paths during drawdown. In the same profile slicken sides, the polished and striated shear planes that form when swelling clays expand and contract increase in frequency, where wetting is recurrent and drying is seasonal rather than prolonged. Together, these features indicate the water is present often enough to reorganize minerals, yet not so constantly that the profile becomes a permanent saturated mass. The rhythm is one of repeated wet pulses over a soil that still breathes between storms. Pedogenic carbonates respond sensitively to that rhythm. In dry to semi-dry ground, evaporation draws dissolved calcium and bicarbonate upward by capillary action and leaves nodules and hard layers that coalesce into thick horizons. Under stronger rainfall, downward percolation dominates, and these carbonate accumulations thin fragment or fade out as ions are flushed past the zone of formation. Where carbonate does persist, it shifts towards small nodules and thin rinds around roots rather than broad indurated sheets. In deeper, well-drained positions, carbonate may still gather at the base of the profile, but lower concentrations and diffuse boundaries speak to shorter residence times for water at those depths. In very humid settings, carbonate can be nearly absent and is replaced by iron and manganese features that cycle with perched saturation. This progression from robust carbonate bands to sparse nodules to near absence marks a tilt in water balance and becomes a reliable field indicator when traced across a basin from leeward slopes into wet corridors. Clay mineral assemblages register the same shift. Under strong leaching in warm, humid conditions, kaolinite, a stable end member with low capacity to hold exchangeable cations, becomes common, while under moderate leaching and episodic drying, smectite and mixed layer clays persist. Across many late Triassic basins, fine-grained intervals that align with wet phases carry higher proportions of kaolinite relative to smectite, and those beds alternate with more smectitic layers that formed during briefer, drier returns. The kaolinite-rich strata sit with clay colours, clay skins and few carbonate nodules, whereas the smectitic beds sit with redder hues and patchy carbonate. Because clay controls how soils swell, shrink and transmit water, this mineralogic pattern also feeds back on slope behaviour. Kaolinite-rich horizons tend to be firm and well-drained, while smectite-rich layers swell during wet pulses and produce shallow slips that move thin sheets of soil into hollows. Microscopic soil textures extend the evidence. Root traces form branching networks that cut down through horizons and terminate as fine filaments. In wetter belts, these traces are abundant and varied, and their walls carry clay linings or thin iron films that record episodes of saturation and drainage. Peds, the natural clods that give soil its structure, arrange into subangular blocks, and prisms where clays have moved and shrink-swell cycles operate. And these structures stand more clearly in humid profiles, where water repeatedly mobilizes fine material and then allows it to settle into aligned fabrics. Where water tables rise into the profile for long intervals, clay matrices develop with soft grey colours and diffuse boundaries, and iron accumulates along root channels as reddish halos when oxygen returns. Charcoal flecks, the black residues of vegetation fires, still occur in some beds, yet in humid belts they tend to be dispersed thinly and to sit within fine floodplain packages that quickly bury them. A sign that wet seasons close the window for oxidation and allow organics to persist. Palynology. The study of pollen and spores supplies a second independent line of evidence, because the microscopic grains that plants release into air and water accumulate widely and resist decay. Spores are produced by ferns and other spore-bearing plants that often favour moist habitats. Pollen comes from seed plants including conifers and seed ferns, whose tolerances span a range of moisture regimes. In assemblages from wet phases, slides show higher counts of fern spores relative to pollen from drought-tolerant forms, and the diversity of moisture-loving taxa increases. The grains arrive with shapes, wall textures and openings that allow them to be sorted into families and groups, and the totals are expressed as ratios that can be tracked through a core or a measured section. Where the ground is wet for longer periods, the spore-to-pollen ratio rises, and the mix shifts toward forms that thrive in marshes, lake shores and floodplain forests. In drier interludes, the ratio tilts back toward pollen from plants adapted to open seasonally dry ground. Because these grains are carried by wind and water, they integrate signals across landscapes and are not limited to the precise spot where they are buried. Even so, the nearby vegetation exerts the strongest pull on the counts in riverside muds, lakeside silts and delta plain clays. The character of organic residues in the same sample strengthens the picture. Planifaces, the mix of spores, pollen, wood fragments, cuticles and amorphous organic matter, tilts toward leaf cuticles, delicate tissue films and gel-like amorphous material in quiet, low-oxygen waters that persist through long, wet seasons. Coarser wood fragments still appear, yet they're more abraded and less concentrated, where floods recede into broad wetlands rather than onto bare bars. Under microscopes, these faces show rounded phytoclasts with smooth edges from prolonged suspension in standing water, and they are interleaved with thin silt laminae that reflect repeated settling in calm basins. In river levee and crevasse deposits, Palinofaces becomes more mixed, yet still holds higher spore content and abundant cuticle when wet ground spreads across plains. Leaf surface traits add a delicate proxy for water availability. Stomata are the minute pores through which leaves exchange gases and water vapour, and in some lineages stomatal densities and indices vary with ambient conditions during growth. In wet sequences, leaves from lakeshore and floodplain plants often show traits consistent with high water availability, including thicker cuticles that resist prolonged wetting and epidermal patterns that tolerate shaded humid air. These signals are subtle and vary among taxa, so they are used alongside the broader palynological counts and soil features rather than alone, yet they align with the direction toward greater humidity where other lines already point. Geography retains its control, along lowlands near coasts and in interior basins with gentle slopes. Paleosols display strong glaying mottling and clay translocation, and palynological samples from adjacent sediments carry high spore counts and abundant amorphous organic matter. On uplands and leeward slopes that sit in rain shadows, profiles keep carbonate nodules and show fewer redox mottles and pollen from drought. Tolerant forms remains a larger share of the count. In between along foothills and broad Piedmont belts, soils show mixed signals in stacked arrangements that reflect upslope inputs of sandier material during peak flows and longer wet intervals between them that allow clay skins and mottles to grow. Through time, these indicators repeat in ordered packages rather than appearing as single markers. Stacks of reddened, leached paleosols with clay skins and diminished carbonates alternate with thinner carbonate-bearing profiles that mark short returns to drier balance. In adjacent lake beds, laminated muds show corresponding shifts in palinofaces and spore-to-pollen ratios, and in river plains, crevasse splay sheets that cap soils carry grain coats and organics that match the wetter state of the ground they cover. Each repetition sets the cadence of wet seasons within the longer humid tendency, and the fine-scale agreement across soil features and microfossil counts anchors that cadence to processes at the surface. All of these observations remain within ordinary behaviour under a shifted climate. Rocks weather to soils. Soils reorganise clays and oxides as water moves. Plants shed spores and pollen. Grains are carried and set. In a world with more frequent rains, the balance among these steps favours features that require persistent moisture. Glade matrices, iron mottles, clay skins, abundant root traces, palan are facies rich in cuticles and amorphous organic matter, and high counts of spores from moisture-loving plants. Where dryness returns between wet spells, carbonate nodules reappear reds, brighten smatitic clays thicken and pollen from drought-tolerant forms rises. The ledger these materials keep is explicit and local, yet it scales across basins because water is the common agent that links each sign from the grain that coats a pore wall to the spore that rests in a thin clay lamina. Vegetation responds to the wetter warm seasons with changes that are first visible in the smallest archives and then in whole landscapes, and the pattern holds across many basins with local variations tied to relief and soils. In palynological counts that directly neighbour paleosols and floodplain muds, moisture-loving spores rise and remain high for long sequences, while pollen from dry ground specialists declines or holds only in leeward belts. Ferns spread along lake shores, back swamps and levees, laying a green fringe that thrives on frequent wetting and quick burial by thin sheets of silt. Horsetails take root in shallow channels, and on splays their jointed stems tolerating seasonal flooding and soft ground. Seed plants reorganize as well with broad belts of conifers and seed ferns shifting in composition and stature, where humidity remains high through the growing season. On well-drained ground near foothills, tall conifers assemble into closed stands with layered canopies, cooler understories and deep litter that buffers soil moisture. Along lower plains, mixed floodplain forests organize around water level with willow-like forms and seed ferns near channels and sturdier conifers stepping upslope onto levees and natural mounds. In this arrangement, light heat and water combine to lengthen growing periods, and root networks knit floodplain muds into firm matrices that store water and slow evaporation between rains. Peat accumulation resumes in settings where it had been rare or absent for long spans, and this return is plain in basins that hold broad floodplains with modest gradients. Peat forms when plant production exceeds decay in wet, low-oxygen ground, and in these wetter seasons shallow water tables linger through much of the year beneath dense canopies and sedge-rich mats. In back swamps and abandoned channels, decaying leaves, stems and roots build centimetre by centimetre into spongy layers that resist oxidation, except during short dry pauses. Where peat survives, later compaction and burial coal eventually forms. In the late Triassic frame of these belts, the immediate sign is organic rich mud and fibrous peat, with stems and leaf mats preserved in place. These beds can be traced laterally into levee and crevasse deposits, where silt alternates with peat laminae, indicating frequent overflows that supplied fine clastics without fully draining the wetland. Farther landward in shallow basins perched behind subtle, topographic sills, wide peat mires spread fed by groundwater and seasonal floods, and their surfaces dome slightly where peat growth outpaces subsidence. At their margins, small channels cut and deliver oxygen, rich water during peak stages, but between peaks the water table rebounds and plant communities recover, keeping decay slow. In this way, a coal-bearing facies belt reappears across regions that previously recorded only red soils and thin overbank sheets for long intervals. Plant functional types sort along moisture gradients that have shifted toward the wet end. Needle-leaved conifers with robust resin systems and thick bark persist on well-drained rises, and on coarse levees where periodic flooding buries roots, but does not keep the ground saturated for long. Broad-fronded ferns, seed ferns, and marsh herbs occupy lower ground that remains wet for months, and sphenopsids line shallow channels and waterlogged flats where shifting currents and soft mud would uproot trees. Tree ferns climb where groundwater stays shallow but not permanently at the surface, building rigid trunks that lift fronds into light above mats of herbs. In places where water flows from springs fed by karstic uplands, tufa-coated roots and stems testify to steady seepage and low-energy deposition beneath shaded canopies. On floodplains that sit within reach of frequent crevasse events, pioneer communities of opportunistic shrubs and herbs spring up after each splay and then give way to mixed forests as channels shift and water tables stabilise. The turnover is not everywhere synchronous, and in leeward interiors behind high ranges, some sectors retain dry-adapted plant mosaics with thicker cuticles and leaves shaped for water conservation. Yet even there, the edges of wetlands intrude farther into hollows and along valley trains than before. Plant growth habits feed back on the ground and the air in ways that reinforce the humid balance without creating new drivers. Dense canopies shade soils and keep afternoon temperatures lower at the surface, slowing evaporation and keeping litter moist. This favours fungi and microbes that build stable aggregates and occlude organic matter within clods, which in turn reduces the rate at which pulses of rain detach and carry soil. Root mats along banks resist erosion during moderate rises and direct water into subsurface paths that lengthen the time of saturation behind levees. Transpiration returns water to the boundary layer even after rain has paused, supporting afternoon convection over plains downwind of forests. In mires, mosses and low herbs trap fine clastics and build surfaces that rise with sediment input, preventing drowning and allowing peat to continue forming despite frequent silt drapes. On sandy levees and bars, conifer seedlings establish on moist seedbeds left by waning floods, and their survival rates increase when the next wet season arrives early enough to avoid prolonged desiccation. Plant remains record these arrangements with detail that scales from cells to landscapes. Leaf impressions lie in thin clay partings, their venation clear, and their cuticles preserved where burial was quick and oxygen low. Wood with growth rings that widen and narrow with season length, and water availability becomes more common in floodplain scrolls, where trees survived many years of repeated overbank flows. Root traces pierce paleosols extending downward to water tables that rose and fell, and are sometimes ringed by iron halos where oxygen returned with drawdown. Amber appears in small amounts in some conifer belts as resin that dripped and hardened later to be buried among needles and twigs, though its abundance varies with species and setting and does not serve as a universal marker. Litter mats stand in quiet water and are covered by event layers of silt that record short floods. Between events, microbial films bind leaves and stems, and thin carbonate rinds precipitate in shallow shaded pools during still hours. In peat plant tissues collapse and gel, but fragments of cuticle and spores survive, and their mix skews toward forms that prefer shade and wet ground. Productivity increases on average where soils deepen and water is reliable, yet the mode of production shifts towards storage in peat and wood, rather than rapid turnover in thin, dry soils. In floodplain forests, tall conifers and seed ferns add wood mass each year and drop large volumes of litter. Some of that litter moves into channels during floods and builds log jams that deflect currents and seed new levees downstream. In mires, slow-growing herbs and shrubs add little wood, but continuous matting of leaves and stems builds peat that keeps pace with subsidence until rare erosive phases clip the top and distribute fragments across nearby flats. This combination of increased production and improved preservation under low oxygen conditions explains why organic-rich intervals thicken during wet sequences, even if production per unit area does not rise sharply everywhere. Uncertainty remains about the exact timing and identity of taxa that dominate each belt in every basin, because exposures are uneven and preservation is patchy, yet the shared trends across well-studied regions are strong. Moisture-loving plants become more abundant and widespread. Community mosaics reorganize so that wetland belts expand and upland belts adjust their species mix toward forms that tolerate higher humidity and shorter dry seasons. Coal-forming wetlands reappear in multiple basins and persist through repeated wet sequences, though they still shrink during shorter drier returns and remain absent in some leeward interiors. These trends align with the soil and palynological signals already noted and with the sedimentary signs of frequent overbank flows, and together they mark a vegetation system that has shifted its average position toward the humid side of its long-held range. Landscape patchiness ensures that not all signals are uniform. Along coastal plains with wide accommodation and gentle relief, peat mires grow broad and coalesce into long belts that parallel the shore before breaking around distributary networks. In intermontane basins, wetlands fill floors, while conifer forests climb lower slopes beneath a canopy broken by landslides and fans that reset succession. On high plateaus with shallow soils, open woodland mosaics persist with low stout conifers that tolerate seasonal frost and moderate summer rain, and peat forms only in protected hollows. The persistence of these variations underscores that the driver is not a new climate regime but a shift within the same framework toward more frequent rains and longer wet ground. The result is a clear reorganization of plant life across Pangaea's humid belts. During this interval, wetlands widen, floodplain forests thicken, peat forms, again where space and water allow, and even dry-backed regions accept a greater share of wet ground along their margins. The archives that keep this story are direct and proximate to the processes that shaped them. Spores and pollen that fell from the plants themselves, soils moulded by water that those plants shaded and fed, plant tissues buried whole in muds that waters carried and peat that formed where waterlogged ground slowed decay. In this way, the vegetation shift records the hydrological tilt of the age with living structure and with the quiet return of thick organic layers that will under later burial yield coal once more. Terrestrial animal communities reorganize as wetter, warm seasons reshape ground, cover floodplain geometry, and the timing of water on the land, and the changes unfold as a series of measured shifts rather than a single break. Herbivores that depend on low soft plants expand along lake shores, marsh edges and crevasse belts, where ferns and horsetails now stand dense for many months each year, and browsers that favour tougher foliage occupy levees and well-drained rises, where conifers and seed ferns persist. In many basins, the most conspicuous plant-eaters of earlier intervals wane as their favoured open, seasonally dry flats contract. Rhynchosaurs, robust herbivores with deep skulls and shearing jaw batteries, become less common in several successions that cross the wetter phase, while other archosaur lineages with more flexible feeding and locomotor habits appear more frequently in the same beds. This replacement is not uniform across regions because each basin holds its own mix of habitat and relief, yet the shared direction toward wetter ground sets the stage for new ecological arrangements to take hold. Amphibians respond quickly to the extended presence of surface water. Large temnospondyls whose life cycles tie to ponds oxbows and slow channels leave more frequent traces in floodplain and lake margin sediments, including bones in laminated muds and trackways on firmed silt skins that formed between floods. Their distribution widens whenever wetlands connect, and larval habitats persist longer into the warm season, where high water tables keep pools from drying. Small amphibian precursors also benefit from shaded humid forest floors and from the fine litter that now blankets floodplains beneath closed canopies. In these belts, amphibian diversity and abundance rise in step with wetland expansion, though high flow pulses still limit their hold on active bars and levee tops. In river corridors that remain flashy, amphibians cluster in backwaters and spring-fed pockets where recharge holds steady through dry spells. Insect faunas track vegetation and moisture. Winged forms that feed on spores, pollen, and soft leaves find stable resources across a longer growing season, and traces of herbivory on leaves increase in quiet floodplain beds that bury foliage rapidly. Aquatic larvae of insects occupy shallow channels and marsh pools in greater numbers, and their exuviae accumulate in thin laminae that settle in the lee of low bars. Overland termite-like decomposers expand with the rise in plant litter, building small mounds and galleries whose infill later forms distinctive soil structures. These shifts filter upward through food webs and provide steady prey for small vertebrate predators that patrol edges between wet ground and firm levees. Among reptiles, crocodile line archosaurs diversify along the interfaces of water and land. Phytosaurs, long-snouted semi-aquatic predators that resemble modern crocodilians in habit, though not in close relation, continue to dominate many channel and lake margin assemblages and leave abundant teeth and armour in near-channel sands. Other pseudo-Suchians, including forms with heavy armour and more terrestrial habits, persist on higher ground and along fan toes where drainage remains brisk. In the same successions, two-legged theropod dinosaurs and small dinosauriform relatives appear more frequently through the wetter interval, first as scattered bones and tracks, and then as recurring elements of floodplain and levee faunas. Their remains co-occur with early armoured ornithischians in some basins, and with small sauropodomorphs in others, suggesting that a range of plant-eating and meat-eating roles begins to reorganize as habitat belts widen and connect. The timing of this diversification relative to the wettest phases varies by region because stratigraphic completeness and dating precision differ, yet several well-dated sections align the early spread of dinosaurs with the interval of stronger rainfall and the reshuffling of dominant herbivores. Mammaliaform precursors and their cynodont relatives continue as small insectivores and omnivores in understories and burrow systems, making use of the damp-shaded ground that now covers much of the floodplain. Their teeth, with differentiated cusps suited to varied diets, occur in microvertebrate concentrations, where small bones and teeth collect in crevices, hollows, and the beds of quiet pools. Burrow traces in some paleosols show repeated excavation and fill cycles that match the cadence of wet and dry phases, and in these levels the small bones of cynodonts and other burrowers increase. The pattern suggests that humid ground does not hinder subterranean life. Rather, it supplies steady food and tolerable temperatures beneath dense plant cover. Large terrestrial predators adjust to the new layout of prey and ground. Rauisuchians and other large pseudosuchians remain apex hunters in several basins, but their trackways shift away from formerly open plains toward levees and firm rises that skirt wetlands. Theropod dinosaurs, lighter and more cursorial, leave narrow tridactyl tracks on damp levee tops and splay caps, and appear in assemblages that also hold abundant amphibians and small reptiles. Where levees breach and build repeatedly the patchwork of firm ground, and wet depressions favours predators that can move quickly between habitat patches, and the record there shows mixed guilds rather than a single dominant form. Turtles and early relatives expand in quiet waters, and on marsh margins their shells and limb bones accumulating in channel lags and crevasse splay tails that briefly pond water. The structure of floodplain forests influences where animals feed and move. Closed canopies reduce understory heat and offer cover for small vertebrates. Climbers and gliders benefit from continuous tree crowns, and their remains and tracks appear in fine floodplain clays that once received leaf rain and rare silt sheets. On levees and natural mounds, the mix of tree height and spacing shapes prey visibility, and predator approach paths and trackway density increases on these firm, lightly vegetated surfaces after floods lay silt that later hardens into thin crusts. In mires where peat grows heavy, animals avoid deep mats except during drought windows, so their traces skirt margins where sedge mats grade into rooted forest hummocks. In these belts, the archival record consists more of shed elements and drifted bones than of in situ skeletons because decay is rapid at the surface, and burial favours the small and the quickly covered. The ecological restructuring is not a simple replacement, but a redistribution across hydrologic and vegetational gradients. Herbivore guilds sort along water availability, with soft plant feeders clustering in wetlands and mixed feeders patrolling levees and well-drained rises. Predators take positions that exploit the edges of these belts. Amphibians occupy the wetter cores and link aquatic and terrestrial energy paths. Insects feed on the new abundance of soft tissue and spores and carry energy upward to small reptiles and mammalia forms. This web is dynamic at seasonal scales as water rises and falls, and at longer scales as channels avulse and wetlands grow or shrink, and the fossil record captures that dynamism in stacked packages of trackways, bone beds and microvertebrate lags tied to depositional events. Several uncertainties attend the exact pacing and causal chains within these changes. Radiometric dates are sparse in some regions, and biostratigraphic markers can lag environmental shifts, so the appearance or disappearance of a lineage in a given section may not align perfectly with the wettest pulses. Some basins show prolonged coexistence of earlier dominant herbivores with new entrants, while others show a quicker turnover, likely reflecting differences in relief soil and plant community. What remains consistent is the direction of change where ground moisture rises and wetlands expand. Amphibians more common wet ground, insect traces, more frequent semi-aquatic predators, steady or rising dry ground, herbivore specialists contracting in footprint, and small dinosaurs and their kin appearing and recurring through the record. The skeletal and ichnological archives mirror this spread. Trackways show increased diversity of bipedal prints on firm silt skins, long continuous lines from semi-aquatic predators, crossing bars and dense clusters of amphibian tracks on the margins of waning pools. Bone concentrations in crevasse tails and floodplain hollows include mixed assemblages of small to medium vertebrates transported short distances by sheet floods that followed seasonal rains. In lake margin beds, articulated amphibian skeletons lie in laminated muds, where low oxygen favoured preservation, and isolated reptile bones, and teeth occur in thin silt lenses that settled from dilute turbidity currents. Across multiple basins, these repeating motifs align with the broader signals of a hydrological cycle that now runs faster. In some, the terrestrial fauna during this interval adjust to a world with longer wet seasons, higher water tables on plains, and thicker belts of soft vegetation. The reorganization enhances the share of animals that use wetlands directly or hunt along their margins, maintains or redirects lineages adapted to firm ground toward levees and rises, and admits early dinosaurs and their relatives into a mosaic that now offers sustained prey bases and varied pathways. Regional differences in timing remain, and some interior leeward sectors retain older structures longer, but the common thread is a steady process-based shift in habitat and resource distribution under wetter air and more persistent surface water written into the rocks by tracks, bones, and the fine laminae that settled from floods across the reshaped plains. Marine ecosystems adjust to warmer, fresher, and more turbid surface waters, with responses that track the physics and chemistry already in place, and the clearest ecological signals appear, where light salinity and carbonate saturation shift together. On inner to middle shelves, reef builders and carbonate producers face more frequent interruptions as freshwater lenses and suspended silts dim the photic zone, and as the saturation state for carbonate minerals falls modestly from prior levels. Framework building corals and calcareous sponges grow more slowly and spend longer intervals recovering after storm turbidities and river plume intrusions. In many basins, these intervals of stress open space for microbial mats and microbialite builders that tolerate variable clarity and salinity, and their laminated domal or thrombolytic structures spread across bank tops and in sheltered lagoons. The reef factory does not vanish, but its share of habitat contracts and its continuity breaks into patches separated by low-relief microbial crusts and mixed sands. Where outer ramps and bank crests remain clear and well lit, skeletal sand production continues, yet even there small chemical pushes against saturation and repeated light reductions shorten the season of peak growth and reduce the export of bright sands into back reef flats. Benthic communities on soft substrates reorganize along gradients of oxygen and fine sediment input. On inner shelves beneath plume, influence filter feeders that prefer steady low turbidity currents yield space to deposit feeders that tolerate repeated silt draping. Bioturbation. The mixing of sediment by animals declines where oxygen minima thicken upward into shelf depths during calm seasons, and laminated silt and clay accumulate with only sparse burrow overprints. Where oxygen persists in a thin layer across the bottom, traces become shallower and simpler, recording brief windows of activity between quiescent episodes. Bivalves that tolerate variable salinity and low oxygen gain, and their thin shells scatter in storm-winnowed lags along shore-face thalwegs and in channelized inner shelf swales. In contrast, outer shelf and upper slope settings that remain ventilated continue to host more diverse burrow networks and steadier filter-feeding faunas, though here too fine drapes become common after wet months and mark a shift in background sedimentation that residents must clear during recovery. Planktonic communities feel the combination of longer stratified seasons, modest nutrient injections near fronts, and the slow spread of low oxygen layers below. In nearshore belts and along shelf fronts where riverborne phosphorus and silica arrive, blooms of phytoplankton recur more often during warm months. Their composition varies with clarity and mixing with siliceous forms favoured where silica is abundant, and where shear supplies enough turbulence to hold cells in light, and with other groups favoured in calmer, clearer patches. The organic rain from these blooms feeds the upper parts of the oxygen minimum zone and steepens redox gradients at mid-depth. Offshore, in clearer waters, steadier stratification holds producers in the photic zone through long intervals and supports moderate continuous production rather than sharp pulses. Radiolarian assemblages sensitive to temperature and nutrient structure in the upper water column shift in species makeup across some basins during the wet interval, with forms that favour warm stratified layers becoming more common, and horizon preferences climbing slightly in step with the shoaled thermocline. Their siliceous skeletons settle into mid-depth water, where dissolution and remineralization operate, and a larger share reaches the seafloor in laminated packages where oxygen is low. Nekton and pelagic invertebrates follow food and oxygen corridors set by the layered water column. Ammonoids with planktonic young and mobile adults show turnovers in several successions that cross the wetter phase, with some lineages declining and others rising in abundance and range. The timing of these changes varies across regions, yet multiple well-preserved sections place diversity and dominance shifts within the span of sustained rainfall, and stratification rise consistent with altered productivity and oxygen structure. Thin-shelled pelagic bivalves spread broadly in some basins and leave widespread shell pavements in dark mid-shelf shales, marking waters that remained quiet and low in oxygen for long intervals, but still received steady surface production. Fish communities reorganize as well, with small planktivores tracking blooms along shelf fronts and larger predators following them. Their scales and bones accumulate in condensed horizons on outer shelves, where bottom currents later concentrate light material during brief ventilated phases. Marine reptiles remain apex hunters along some margins, and their bones and teeth occur in bone beds that form at breaks in sedimentation on ramps, yet their signal is sparse relative to the fine-scaled archives of invertebrates and plankton. Reef crisis signals present in multiple margins reflect the sensitivity of framework builders to combined stressors rather than to a single cause. Light limitation during turbid seasons shortens the daily window for photosymbiotic corals. Freshened caps and variable salinity impose osmotic strain in lagoons and back reef pools. Lowered saturation increases the energetic cost of calcification. Each stress alone can be weathered for short intervals, but together and repeated across seasons they reduce net accretion and open more substrate to colonization by microbes encrusting algae resistant to turbidity and opportunistic bivalves. Where storms pass, rubble fields show slower consolidation into rigid frameworks, and long-lived heads that once tied beds together become rarer on inner banks. Outer banks retain bright shoals and sand waves, yet their sand supply to interior flats slackens, as passes spend more days with hazy water and weaker light. Pelagic redox structures reinforce these ecological patterns. A thicker oxygen minimum constrains vertical migrations of zooplankton and nekton that normally dive by day and rise at night. Migrations compress into shallower layers, concentrating prey and predators and increasing encounter rates for part of the day, while depriving deeper layers of grazers. When the compressed layer coincides with fronts, surface productivity can be grazed efficiently and turned into fast-sinking fecal pellets that fuel further oxygen, drawdown below reinforcing the minimum in a gentle loop. Where the minimum shoals onto the shelf. During calm seasons, benthic animals find only brief windows of high oxygen after storms deepen, mixing, and their traces become episodic stripes in cores rather than continuous fabrics. The balance shifts back toward more persistent benthic activity whenever gateways ventilate and when wet seasons end, but the long average tilts toward quieter bottoms under a heavier rain of organic matter. Pelagic carbonate and silica cycles adjust to these biological and chemical settings. In warm, clear sectors, planktonic carbonate producers continue to build thin shells that settle and dissolve along predictable horizons, where saturation drops with depth, and the depth of rapid dissolution shoals slightly as interior waters gain dissolved carbon from respiration. Siliceous production increases along nutrient-rich belts and on some outer shelves. Radiolarian-rich intervals thicken in basins with strong stratification and steady surface production. The rivalry between carbonate and silica is local rather than global in this frame, and many basins show intercalations where carbonate-rich layers alternate with siliceous or clay, rich beds as fronts and atmospheric patterns move productivity belts across a margin from season to season and from year to year. Food webs reorganize without wholesale novelty. Primary producers occupy layered niches set by light and mixing. Grazers track those layers and pulse in abundance where blooms recur. Suspension feeders on the bottom do better where currents regularly sweep fine drapes and where oxygen remains adequate. Deposit feeders dominate where mud blankets persist. Reef frameworks lose ground on inner shelves and persist on outer banks while microbial fabrics colonize stressed interiors and bind loose sediment into low-relief buildups. Predators in the water column follow fronts and compressed migration layers, and their remains concentrate in condensed sections that register the waxing and waning of bottom oxygen. Through it all, geographic variation remains strong sheltered Tethyan subbasins, with narrow gateways amplify low oxygen and fine drape signals. Open panthalacene margins retain broader ventilated belts and steadier skeletogenic sands. Island arcs create pockets of clear water that hold small reef refuges even during wet phases. Uncertainties persist in the exact sequence and magnitude of each ecological shift. Because exposures differ, ages can be imprecise, and ecological signals lag or lead physical drivers by seasonal to decadal scales. Even so, the shared direction across many sections is robust. Inner shelf carbonate factories decline in continuity and give space to microbial and mixed sediments. Benthic bioturbation wanes where low oxygen lingers and laminated beds become common. Plankton communities adjust to longer stratified seasons and to nutrient fronts fed by runoff, with shifts recorded in siliceous and organic microfossils. Pelagic invertebrates turn over in composition and range within the same interval that benthic changes accumulate. These are the ecological expressions of a surface ocean that is warmer slightly, fresher, and more stably layered, and of an interior that exchanges with the air more slowly, and they appear in the record as mosaics of patches stitched together by fine laminae thin shell pavements, microbial crusts and interrupted reef growth across the shelves, and ramps that rim Pangaea. Volcanism supplies a recurrent external push during this interval, and its effects pass through the air, the land surface and the oceans along pathways already in place. A large igneous province grows in the region later called Rangelia, where repeated eruptive phases pour basalt across broad tracts and feed gases to the sky through fountains and fissures. The gas mix includes carbon dioxide and water vapour that endure in the air sulfur dioxide that converts to fine sulfate droplets within days, and halogens that alter upper air chemistry for short spans. Carbon dioxide adds to the long-lived greenhouse reservoir and warms the lower atmosphere by raising the downwelling infrared energy that returns to the surface. Water vapour rises as a feedback since warmer air holds more moisture and evaporation increases over warm seas. Sulfate aerosols scatter sunlight and cool the ground for months to a few years after each large pulse, but they fall out or convert to less effective forms on timescales shorter than a decade, while carbon dioxide lingers for much longer. The alternation of brief dimming and prolonged warming does not create a sawtooth in climate records at the seasonal scale, because many processes blur short spikes, yet at the scale of years to centuries, the combined signal leans warm and moist, and the hydrological cycle runs faster where geography invites ascent. Fine ash settles across basins downwind of vents and drapes, soils, lakes and shelves with thin layers of glass shards that weather quickly in warm, wet ground. On land, ash dissolves and releases potassium, phosphorus and silica that stimulate plant growth and modify soil horizons. In lakes and coastal seas, ash temporarily dims water and supplies micronutrients that can prompt short blooms once clarity returns. Coarser Lapillian bombs fall near sources and build local cones and blankets that later break down and enter rivers as sand and gravel. Between large eruptive phases, smaller degassing and lava effusion continue to add gases without thick ash, extending the time during which the atmosphere carries an enhanced carbon load and during which soils and waters receive small but steady inputs from weathering of fresh basalts. Aerosol fields shape clouds while they persist. Fresh sulfate particles seed droplets that can brighten clouds and lengthen their life, especially over oceans where background nuclei are fewer. Over land, a wetter surface tends to curb dust emission, so the decline in fine mineral dust during wet months shifts the balance of nuclei towards sea salt and biogenic particles. These microphysical changes vary with storm type and air mass, but combine with higher humidity to favour more frequent light to moderate precipitation, rather than fewer heavy downpours, especially along corridors of low-level convergence. In cold layers aloft, volcanic aerosols can warm the lower stratosphere for short spans, adjusting stability near the tropopause and modestly redirecting jet position, yet these effects fade as particles settle and as chemistry returns to background. The carbon cycle receives both inputs and new pathways for drawdown. Carbon dioxide from degassing increases the atmospheric reservoir and dissolves into surface waters where it shifts the balance among carbon species toward more dissolved carbonic acid and bicarbonate and lowers carbonate ion concentration. In coastal seas, this chemical tilt joins freshening by runoff and a higher dissolved carbon load from respiration to push carbonate saturation slightly downward, raising the energetic cost for calcifiers and helping explain the reduced continuity of carbonate platforms on inner shelves. On land, the same enhanced carbon load and warmer, wetter conditions accelerate chemical weathering of silicates, a process that consumes carbon dioxide as bicarbonate forms and carries cations to the sea. Over thousands to tens of thousands of years, this drawdown acts as a negative feedback that pulls the atmosphere toward a new balance. During the wet interval, the input from volcanism and the output by weathering and burial of organic matter both strengthen, and the timing of their competition at any one place depends on relief rock type and the depth of soils. In wetlands and floodplains that now stand wet for long seasons, more plant production is preserved under low oxygen and accumulates as peat. When these organics are later buried, they sequester carbon on long timescales. In lakes with high residence time, dissolved carbon rises from both inflow and respiration, and carbonates precipitate less often, a shift seen as thicker siliciclastic laminae and fewer micritic interbeds. In the open ocean interior, added organic rain from sustained surface production increases dissolved inorganic carbon at depth and lowers saturation there, while slower renewal maintains these changes between intrusions of cooler, more oxygenated water. Trace elements move with these forcings and leave markers in sediments that bracket volcanic influence. Mercury emitted during eruptions and transported widely in the air adsorbs onto organic matter and fine particles, and settles to the ground and sea. In many basins, peaks in mercury concentration align with layers that also hold ash shards or altered glass, providing a chemical tie to eruptive phases even where visible ash is scarce. Vanadium, molybdenum and uranium become enriched in muddy beds that accumulate under low oxygen at the seafloor, and their ratios help distinguish between transient and more persistent oxygen depletion. In some sections, charcoal counts briefly rise after ash falls, where surface fires pass through dry belts on lee slopes during short returns to aridity, yet in wetter cores, charcoal remains sparse and dispersed, consistent with humid ground and quick burial. The water cycle amplifies carbon movement under these conditions. Stronger rainfall and runoff deliver higher dissolved and fine particulate loads to the sea, and the riverine flux of bicarbonate and cations increases where basalts and fresh volcanic lastic deposits are exposed. This delivery helps buffer coastal waters chemically, but also spreads the freshened turbid caps that limit light for calcifiers. In soils, higher moisture and organic acids from litter sustain deep leaching that feeds groundwater and streams with dissolved carbon, and in wetlands, methane production rises where saturated anoxic conditions persist. Most of that methane is oxidized in soils and water columns, yet its presence is a local manifestation of the broader redox shift toward reduced states in waterlogged environments. The balance of these processes at any time depends on the pacing of eruptive pulses. A large pulse injects sulfate to the air, dims the surface for a season to a few years, and supplies ash that alters soils and waters quickly. The subsequent years carry the long-lived carbon dioxide forcing that continues to warm and moisten the lower atmosphere. If pulses cluster, the background aerosol load remains elevated longer, and surface dimming extends, though not enough to reverse the hydrological lean, because humidity and soil moisture stay high and carbon dioxide persists. If pulses space widely, each leaves a marker in ash or mercury, and a small step in the long count of carbon that the weathering engine then works down over thousands of years. In either pacing, the lines traced earlier remain. The air grows warmer and more humid on average clouds, and rain occur more often. Surface waters freshen and stratify. Carbonate saturation declines modestly near coasts, and oxygen minima thicken in the ocean interior. Volcanism also leaves physical traces in stratigraphy that tie environmental changes to specific horizons. Airfall tuffs appear as thin, sharply bounded beds in floodplain clays, lake laminae and shelf muds. Altered to clay minerals, they still hold shard outlines and crystal ghosts. Coarser pyroclastic units occur near sources and are reworked by rivers into lens-shaped bodies that fine upward. Basaltic weathering products enrich soils in iron and magnesium and create horizons with distinctive colours and exchange properties, and their spread through catchments can be tracked by the downstream rise of those elements in river clays. On shelves, ash-rich layers couple with storm beds to form event packages that begin with a graded ash cap and pass into rippled silt as waves and currents rework the fallout. These markers punctuate the otherwise steady stacking of wet climate deposits and support the reading of cores where they coincide with shifts in shelf ecology and with evidence for stronger stratification in nearby basins. Uncertainties remain in the exact volumes and rates of gas release for each pulse, and in how evenly aerosols spread around the globe, yet the first-order roles are secure. Carbon dioxide adds durable warmth and moisture to the lower air. Sulfate aerosols briefly dim and cool before falling out. Ash modifies soils and waters quickly, and then merges into the background of clays. Basalt weathering accelerates carbon drawdown and cation delivery. Redox-sensitive elements record intervals of low oxygen in the sea. These linked responses translate eruptive activity into a sustained push on the carbon and water cycles that aligns with the wetter seasons already described and helps explain the joint appearance of freshened surface waters, dimmed inner shelves, and thicker oxygen minima beneath them during this 2 million year span. Isotope records and stratigraphic markers fix the duration and pacing of the wet interval by tying scattered observations to measurable signals that repeat across basins. A carbon isotope excursion is a shift in the relative abundance of the heavier carbon isotope to the lighter one in carbon-bearing materials, and during this episode multiple negative excursions appear in both marine and terrestrial archives. In shelf limestones, the ratio measured from carbonate muds trends toward lighter values in several steps separated by quieter intervals. In coeval shales and coals, carbon bound in organic matter shows the same general tilt. Lighter values point to injections of isotopically light carbon to the surface reservoirs and to burial imbalances that remove heavier or lighter fractions at different rates. The important point in these sections is the repeated character rather than a single swing. Small to moderate drops recur and bracket intervals of stronger rainfall and platform stress already described, allowing workers to trace line by line where the humid phases sit within thicker stacks of sediment. Because carbon in plants and seawater responds together to large system pushes, matching shapes in carbonate and organic curves help align marine shelves with floodplains and lakes even where fossils are sparse. Osmium and strontium isotopes provide additional constraints because they respond to different sources. Osmium in marine muds can carry a pulse of unradiogenic values. When volcanic aerosols and ash deliver mantle, derived metals to the sea, and several basins capture short spikes that sit near ash-rich horizons and near the starts of light carbon intervals. Strontium in seawater tracks long-term balances between continental weathering and seafloor processes. During wet phases, stronger river weathering can nudge seawater toward more radiogenic strontium, and carbonate beds that grew in clear windows record that tilt. Sulfur isotopes in marine sulfates and pyrite speak to redox conditions in the water column and sediment, where oxygen minimum layers thicken, and sulfate reduction in pore waters intensifies the fractionation between sulfate and sulfide can widen, and leave subtle trends in sulfate layers and in pyrite formed near the seabed. These proxies vary in sensitivity, and may not move together at every site, but when several shift in the same order around ash, mercury and carbon signals, they tighten the timelines that separate one wet pulse from the next. Radiometric ages bracket the episode by dating volcanic layers that fall within or immediately beside the relevant strata. Zircon grains in thin tuffs yield uranium-lead ages with errors small enough to anchor long million-year scales, and where two or more dated beds sit above and below carbon isotope steps. The elapsed time between them can be measured directly. In sections that include ash linked to the large igneous province, those ages provide maximum or minimum constraints on the timing of gas release and aerosol pulses relative to the wet phases. In other basins, reworked ash complicates the picture by mixing older and younger crystals. In such cases, careful selection of the youngest coherent zircon population sets the closest bound. Across multiple margins, dated tuffs and correlative markers align with a total duration of roughly 2 million years, and place the onset in the middle part of the late Triassic consistent with the framework already established for the rainfall increase. Magnetostratigraphy adds a global ruler by recording reversals of the planet's magnetic field in the remnant magnetization of sediments. Muddy beds and fine limestones acquire a stable magnetic signature as they form, and the up and down sequence of normal and reversed polarity can be matched to a reference scale. Where lake and shelf sections carry long undisturbed polarity trains through the interval of isotope change, those trains help tie basins to one another and to the broad time scale even where radiometric ages are sparse. In some successions, polarity boundaries fall close to carbon isotope steps and to faunal turnovers, allowing composite age models that use each tool to refine the others. Uncertainty remains where magnetic overprints obscure primary signals, yet in well-preserved sections the polarity pattern is clear enough to support regional correlations across many hundreds of kilometers. Cyclostratigraphy. The study of climate-paced bedding rhythms refines the internal pacing. Variations in the shape of the planet's orbit and the tilt and wobble of its axis modulate how sunlight is distributed and can imprint regular cycles of tens of thousands to hundreds of thousands of years in sedimentary packages. In lakes with laminated muds, couplets, and thicker bundles stack into groups that match precession and eccentricity frequencies, and spectral analysis of bed thickness or colour can isolate those periods. On shelves, alternations between clay-rich and carbonate-rich layers repeat at scales that fit the same astronomical pacing when accommodation and supply allow continuous accumulation. When such cycles are counted between dated ash beds, they yield high-resolution estimates for the length of wet pulses, the spacing of quieter interludes, and the total number of rainy seasons that fall within the episode. In several basins, these counts reach into the tens of precession beats, and several eccentricity bundles compatible with a total span of about 2 million years, and with 2 or more clusters of stronger change separated by shorter plateaus. Biostratigraphy supplies independent anchors through appearances and disappearances of index organisms that evolve or move ranges quickly. In marine rocks, ammonoid and conodont zones cross the interval, and particular species levels recur at similar positions relative to carbon isotope steps and to laminated low-oxygen beds. On land and in marginal settings, palynological zonations provide equally useful tie points. Shifts in spore and pollen assemblages mark the rise of moisture-loving plant groups, and those shifts coincide with soil glaying and with the first negative carbon steps. Because organisms can lag environment and preservation can fail, these ties carry more uncertainty than radiometric ages. Yet when multiple fossil markers align with isotope and polarity data, the composite framework becomes robust. In some regions, vertebrate biozones that register the decline of earlier herbivores and the spread of new archosaur clades overlap carbon steps and ash layers, offering broad brackets that agree with the finer tools. Geochemical markers that move with water and redox add texture to the timelines. Peaks in mercury concentration coincide with ash, and with the early parts of light carbon intervals in several stacks, consistent with repeated eruptive phases that deliver mercury to air and then to sediment. Ratios of redox-sensitive elements such as molybdenum to uranium rise in laminated shales that formed under thicker oxygen minimum layers and fall in more bioturbated intervals, aligning with cyclic changes in stratification and with riverine nutrient delivery. Calcium to magnesium and strontium to calcium ratios in carbonates vary with river input, and with the mix of carbonate producers and their gentle drifts bracket the slow decline and partial recovery of inner platform vigor. None of these markers stand alone. Together they draw smooth curves that match the larger shape traced by carbon isotopes and by sedimentary facies. Key surfaces in the rock record serve as physical tie lines that repeat across regions. Floodplain stacks include laterally continuous paleosol horizons, with strong clay colours and abundant clay skins that can be walked for many kilometres and placed relative to nearby crevasse sheets that carry thin ash caps. Lake margins show high-stand shorelines that can be mapped and dated by interbedded tuffs and by magnetic zones. On shelves, drowning unconformities and condensed hard grounds develop where carbonate production falters and fine drapes pile up. These surfaces often hold shell pavements and pyrite spot horizons that register low oxygen and can be traced between wells and outcrops. When such surfaces occur near carbon isotope steps and polarity boundaries, They join the chemical and magnetic lines to form composite markers that travel farther than any single proxy can. Putting these strands together yields a structure in which the onset of lighter carbon values ash and mercury peaks early reef stress surfaces and first expansions of gleed soils cluster near the opening of the interval. A second cluster of light carbon and redox signals recurs later, separated by quieter stacks that still carry humid signs but fewer extremes. Polarity trains and dated tuffs bracket the whole to a duration of about 2 million years, and astronomical pacing within the stacks counts out the internal rhythm in tens of precession beats and several eccentricity bundles. Regional differences in completeness and preservation remain, and in some leeward interiors only parts of the pattern survive, yet across many shelves, lakes and plains, the coincidence of carbon-mercury, ash, magnetic polarity, and fossil markers resolves the episode's timing to a level that matches its scale long enough to reorganize hydrology, and ecology short enough to leave clear packages that stack and can be traced from basin to basin. Regional case studies show how the same drivers express differently across basins, and they also mark where uncertainties remain. Along the western Tethys, the platforms later exposed in the Dolomites preserve a detailed picture of inner to middle shelf change. The bright carbonate banks that grow during clearer intervals give way to mixed packages with thin clay drapes, microbial crusts, shell pavements, and short drowning surfaces. Negative steps in carbon isotopes align with these stress surfaces, and with thin ash layers and mercury peaks in nearby basins, and laminated shales appear where low oxygen reaches onto the shelf between ventilated phases. Farther south along the same margin, coeval successions show partial continuity of carbonate production on outer ramps, while inner banks falter, underscoring the role of shelf width passes and river mouths in mediating light and chemistry from season to season. In the Germanic Basin and adjacent Central European basins, continental and marginal marine records stack in alternation. Red beds with paleosols that carry carbonate nodules step upward into grey-green floodplain packages with glaying clay skins and high counts of moisture-loving spores. Lake expansions lay laminated muds with flood couplets, and thin tuffs provide radiometric tie points that sit near light carbon intervals measured in coeval evaporate limited carbonates. Brackish to marine tongues that enter along seaways record muddy laminated belts with simple trace fossils, and thin bivalve pavements, and these belts thicken within the wet interval. The match between soil features palynology lamination and isotope shape is close, yet hiatuses at some sequence boundaries complicate the exact pacing. In South China, mixed carbonate and siliciclastic shelf successions register repeated freshening and light limitation on inner shelves, while outer margin sections keep steadier carbonate sand stores. Radiolarian-rich beds become more common in basinal shales during the strongest wet clusters, and conodont and ammonoid zones cross the same stacks and allow regional ties. Where gateways into basins are narrow and sills shallow, interior waters record thicker low-oxygen packages with redox element enrichments, and where gateways remain deep laminated intervals thin and bioturbation persists. Ash beds and mercury peaks occur in multiple sections, yet the relative size of each peak varies, reminding that aerosol spread and ash fallout are uneven, and that local rain patterns during fallout control how much material enters any given basin floor. On the margins of Panthalassa forearc and backarc basins keep marine records that emphasize interior oxygen structure and fine sediment delivery. Laminated mid-shelf to slope shales expand where stratification strengthens, and shell-rich condensed layers form during brief ventilated returns. Carbonate factory signals are weaker on these margins because shelf width is limited and siliciclastic supply remains high, yet negative carbon steps and trace element enrichments align with those on the Tethyan side. Island arcs and microcontinents create mosaics. Clear pockets retain small reef refugees on windward banks during wet phases, while leeward pockets accumulate laminated muds with sparse traces. Correlation across these pockets relies on ash beds, polarity trains, and carbon curves, rather than on facies alone. In the Newark Basin and related rift basins of eastern North America, lake successions provide high-resolution archives of hydrology. Varved mudstones stack into precession, and eccentricity bundles, and thickness and grain size of warm season layers increase through clusters that align with the light carbon steps measured from organic matter. Shoreline faces show repeated high stands with beach ridge sets and transgressive wave-cut benches and delta lobes prograde rapidly during wet clusters, then pause or retreat during short drier intervals. Palynology shifts towards spore-rich assemblages in the same packages that carry glade paleosols on exposed margins. Radiometric ages from interbedded tuffs and magnetostratigraphy across continuous cores anchor the duration and support ties to marine sections that share the carbon curve shape. In the Ishigalasto and neighbouring basins of western Gondwana, floodplain and channel belts record ecological and hydrologic change on land. Thick overbank silt and clay packages with gley colours, slicken sides and clay skins alternate with crevasse splays that cap soils at short intervals. Plant remains include abundant ferns and floodplain conifers, and organic rich lenses appear where wetlands pond. Vertebrate assemblages through these stacks record the waning of earlier dominant herbivores and the recurring presence of early dinosaurs and their kin, with trackways on splay caps and bones in crevassed tail lags that follow seasonal floods. Dated ash beds constrain the timing, yet exposure gaps and lateral faces changes introduce uncertainty in how quickly the faunal changes unfold within each wet cluster. Across northern Gondwana and the Tethyan Middle East Epiric seas and coastal plains, register the wet tilt with mixed evaporate siliciclastic and carbonate successions. Evaporate cycles thin and pause near the strongest wet clusters as freshening and runoff dilute brines. Marginal seas carry more clay and silt, and inner ramps host microbial mats and thin shell pavements, where frameworks falter. In adjacent continental interiors, paleosols lose carbonate nodules and gain glaying and iron mottles, and palynology tilts toward moisture-loving forms. In some sectors, brief returns to stronger aridity produce thin evaporate or calcrete layers. Within the wet span, a reminder that regional circulation and rain shadows can imprint short reversals on the broader trend. Southern high-latitude records are sparser yet. Where preserved, they show lake expansions, thicker floodplain fines, and plant communities adjusted toward humid ground. In agreement with the lower latitude signal, but with shorter warm seasons that limit peat growth to protected hollows. These case studies also expose sources of uncertainty that limit resolution. Hiatuses at sequence boundaries remove parts of the record in many shelf and continental settings. Reworking of ash introduces older zircon grains that can widen age spreads if not carefully filtered to the youngest population. Diagenesis can modify original isotope ratios in some carbonates, requiring checks against organic carbon and against multiple sections. Magnetic overprints can obscure polarity in some red beds and demand careful demagnetization to recover primary signals. Faunal and floral ranges can lag environmental shifts or respond in step with local thresholds rather than regional means, so biostratigraphic tie points must be cross-checked with independent clocks. Spatial variability is a feature, not a flaw. Narrow gateways' shelf width, relief, and distance from large rivers govern how strongly each basin feels the wet tilt, so some places register bold signals and others only muted ones. Even with these caveats, the alignment of multiple independent lines is striking. In Western Tethys platforms in Central European basins in South China, shelves and basins along Panthalassan arcs in Newark, lakes in Gondwanan floodplains and across northern Gondwana, Epiric seas, the same package of signs recurs during the late Triassic interval in question. Negative carbon isotope steps in clusters, thin ash beds and mercury peaks that frame them, inner shelf carbonate factories reduced in continuity and replaced in part by microbial and mixed sediments, thicker low oxygen packages in marginal and interior basins, soils shifted toward glaying clay skins and diminished pedogenic carbonate, lake high stands and varved bundles that thicken in warm seasons, deltas that prograde rapidly and avulse more often, vegetation that tilts toward moisture, loving forms with peat locally returning, and terrestrial faunas that reorganize along wetter ground. Where signals are weak or missing, the reasons are legible in context-limited accommodation, strong wave or tidal reworking, persistent rain shadow or removal by later erosion. In this way, the variability itself becomes a tool because mismatches invite checks of geometry gateways and local supply before age or cause are revised. The regional synthesis, therefore, does not replace the larger frame. It confirms, it shows its limits and marks where questions remain about the exact pacing, the share of cause among volcanism, weathering feedbacks and circulation adjustments, and the distance that each wet cluster extends across latitude. Those questions sit beside strong agreements, and together they complete the picture of a world that spends about 2 million years with a faster water cycle and a reweighted surface ledger, written differently in each basin, according to its shape and its place on the supercontinent's long margins.